of their own, and then subsequently perform a shielded transfer to the intended recipient with the same privacy level as for Zcash transactions today. The transparent issuance allows for the tracking of the total supply of the asset. One simple example of a case where that is necessary is in the case of the issuance of assets that are meant to be finite, such as NFTs. If issuance was private, a malicious issuer could be able to privately generate additional tokens without others' knowledge, which we don't want. As I hinted just before, the ZSA protocol allows for settings where assets are limited in nature and also where they can be issued infinitely. This is done by means of a finalized flag in the issuance protocol. This is set to be false when the issuer does want to keep the option open of creating more assets. At the point where the issuer has generated the number of assets they want to, they set the flag to true. Once that happens, consensus will ensure that further issuance of the same asset is rejected. Of course, it is not possible to reverse the finalization of an asset. Furthermore, the issuance functionality allows one to issue multiple assets of different types in a single transaction. This saves the issuer the trouble of creating separate transactions for every single asset each time they need to generate more assets. That was the 10,000-foot view of issuance, and we'll now move on to asset transfer. As I had mentioned earlier, the asset transfer is fully shielded. Assets will stay in the Orchard anonymity pool, and they have the same privacy guarantees as the rest of the Orchard pool. Transfers of ZSAs will be indistinguishable from those of ZEC, the native asset as well. The ZSA protocol is backward compatible with Orchard. There's support for spending Orchard notes, that is, we can read old Orchard notes. However, new notes will be generated as per the new format, which allows for a gradual move to the new transaction format without loss of utility for anyone. The third aspect of the protocol is the burning of assets. This is useful in settings such as bridges, where you want to reduce the asset amount on redeeming the bridged asset. As with issuance, we allow for multiple types of assets to be burned simultaneously. And of course, this, just as before, the burn mechanism is also transparent so that we can track the total supply. That's the quick overview of the features. For a more detailed dive, I would recommend a look at our talks from ZconV last year, where we described some of the protocol details in more depth. If you look at those videos, we'd like to highlight that they are from 1 year ago, so the code has progressed since then. Furthermore, some of it was tailored to Zcash D, which is being deprecated, and so we are now working with Zebra instead. With this context, we are now ready for the details of our position on different aspects of the ZSA protocol. So let's dive in. The key takeaway is that the ZSA protocol is largely ready, with various small portions being worked on to get it ready for merging whenever that is scheduled. The first aspect is regarding the design. The Zcash improvement proposals, or ZIPs, that we've been working on are ZIP 226 for the transfer and burn aspects, ZIP 227 for the issuance aspect, and ZIP 230 for the changes to the transaction format. We had our main pull request, which was PR 680, merged some months ago, and these zips are now available on the Zcash zips website. Of course, they are still in draft mode, and we have made some small updates post then. These updates will be added to a new PR in the zips repository. However, the design is essentially stabilized with no major changes expected. We made a pass through the Orchard ZSA circuit we had implemented last year, and we have done various optimizations since then. The goal of optimizations is to reduce the proof size, reduce the time to create the proofs, and reduce the time to verify the proofs. There are often trade-offs between achieving all these, and so the aim is to strike a good balance between all of them. We'll now take a look at the result of optimizations we performed in the ZSA circuit. Note that since we now deal with multiple types of assets, there are various different places where we have additional or different checks as compared to the Orchard circuit. So I'm not a fan of having a lot of data on slides, but there really is no better way to talk about optimization, is there? So I won't ask you to really look at the numbers, and I'll try and give a gist of what to look at in this table. First off, what do these rows represent? The first row is the details of the orchard circuit that was already deployed in NU5. We began by just getting all these additional checks in to create a ZSA circuit that was complete and functional. This is the second row, which is before optimization in that table. The final row is the result of our optimization, so after optimizations. So in the circuit before optimization, you'll notice that the number of rows went to 2207, which is above 2048, which is 2 to the power 11. This was one part of the reason for the jumps in the proof generation and verification times that we see there. So the optimizations we performed were able to bring down the number of rows in the circuit significantly. And therefore, we now have pretty reasonable increases in the proof size, proof generation, and proof verification time values as compared to the orchard circuit. We'll now give a very short summary of the optimizations that helped with this improvement. One optimization was regarding the Synsomia hash that is used both in the ZEC and the ZSA cases. There is a portion of the hash that is computed in the same manner for both cases, followed by a diversion towards the end of the computation. We updated the circuit to do the common part of the computation in the same way for both, with a divergence at the point where it was necessary. This was more efficient than having the entire hash portion of the circuit repeated twice. The other optimization we performed was the addition of some rows and an additional column in order to be able to perform shorter range checks more efficiently, which is required within the ZSA circuit. So that's the update on the ZSA circuit. The Orchard ZSA protocol, however, extends beyond the circuit too. So we'll now take a look at that. At a high level, our status is that the updates that we have made to the Orchard crate to make it support the Orchard ZSA protocol are stable and working. They are based over Orchard 0.8, which is the latest version of Orchard. You might notice that last year we were based on Orchard 0.5. So clearly, we are working towards a moving target, and it's often the case that the updates that were made to Orchard upstream end up breaking our code and require revisits to multiple areas to fix things. However, this rebasing is an important and non-trivial part of keeping our code and pull requests ready for merging whenever the maintainers begin that process, which is why we are keen on staying on top of this. One of the other crates where there has been significant ZSA-related change is the Zcash note encryption crate. The ZSA protocol makes a change to the note structure that lengthens the plaintext being encrypted. The ECC roadmap for NU6.2 includes a generalization of the note encryption design to prepare for this change. We have recently submitted a pull request to the Zcash note encryption crate, that's PR2. We are expecting review of that to begin soon, and we'll be glad to see it merging in the near future. Backward compatibility is another piece of the puzzle that's been on our plate for the last many months. We need the ZSA protocol to work seamlessly with Orchard and Sapling and share the Orchard anonymity pool at the same time. The work in this backward compatibility area does the task of allowing the software to be able to read both older notes along with the newer notes and things like that, for example. We'll dive a little bit more into the specifics now. We'll start with the Zcash note encryption crate. So, like I mentioned, the vanilla Orchard note structure is 564 bytes long. And in the Orchard ZSA note, we have to now include details of the asset base, whether it is native ZEC or otherwise some custom asset. That has to be included in every note. This adds 32 bytes to the note structure, which makes the Orchard ZSA note a total of 596 bytes. The work we did in the PR2 that I mentioned earlier, it generalizes the note encryption code to allow for the encryption of notes of both these lengths in elegant and efficient ways. The next bit is about the Orchard protocol and the changes that we make on the addition of ZSA functionality. We use Orchard bundle to refer to the part of the transaction that encodes the Orchard pool-related information. So the original vanilla Orchard bundle uses the vanilla Orchard notes, which we saw were 564 bytes long. And the zero-knowledge proofs that are generated for verification by consensus are generated as per the Orchard circuit. So the new Orchard ZSA bundle, on the other hand, uses the longer Orchard ZSA nodes. The zero-knowledge proofs are also generated using a different circuit, specifically the Orchard ZSA circuit that I described as optimizing earlier. The circuit performs the various additional checks that I mentioned earlier. We have completed this work, and both bundles are now supported in our pull request to the Orchard crate. This work has been successfully tested against the Python reference implementation for vanilla Orchard, as well as a reference implementation we made for the ZSA protocol. In addition to the expanded Orchard ZSA bundle, the ZSA protocol introduces an additional bundle for the issuance part of the protocol. This issuance bundle contains all the fields of the transaction that are present when assets are being issued. The structure of the bundle looks basically like this. We have issuance actions in these transactions using a terminology analogous to Orchard actions. We look a little bit more into how they are structured really soon, so stay tuned. We also have an issuance validating key, IK, which is a public key for the Schnorr signature scheme that is unique for each issuer. The issuer signs the issuance details into an issuance authorization signature, which serves to validate that issuance was done by the party with the authority to issue those assets. As promised, we'll head back now to the structure of the issue action. The issue action contains an asset description string, which is an up to 512-byte description of the asset that is chosen by the issuer. The issue action also contains a number of issue notes with the details of how much of the asset is going to whom. So as we mentioned a bit earlier in the talk, the issuance procedure is transparent, for which reason the notes are unencrypted and it is public as to how much has been issued and to which address. The last piece of information inside an issue action is the finalize flag. This is used to signal when the issuance of an asset has been completed. Whenever an issue action is spotted, the consensus will involve a check on whether the asset has been finalized previously, with a rejection of the transaction if there is an attempt to issue more assets after the asset has been finalized. So the part of the Zcash code base that we turn to now is the Libra Zcash crate. This contains much of the supporting code that generates transactions and does work on the backend and just basically makes a lot of Zcash tick. Our work on this crate adds support for V6 transactions as specified in zip 230, which is, as we saw, the zip that describes the V6 transaction format. These changes include data structures for the additional and changed components, and also updated computations for the transaction identity and the SIG hash. You might recall that issuance bundles contain unencrypted notes since the issuance process is transparent. Therefore, we have also added support for note serialization in the issuance bundle. Next, we'll consider Zebra, which is the Zcash node that we are going to be using for ZSAs. Here too, we have added support for handling version 6 transactions according to zip 230. Beyond the ability to handle V6 transactions, we also have node consensus code that can handle the changes that come in with V6 transactions and the ZSA protocol. However, one sticking point was that while Zebra performs the consensus checking and transaction handling, it does not generate transactions. So we needed the ability to be able to create transactions so that we could test our changes and additions. We therefore made a tool to generate these transactions. We should highlight that this tool is just for testing purposes. We first built the tool for V5 transactions, that is for vanilla Orchard. We then will have the functionality to create V6 transactions, and that includes both the issuance and transfer of Zcash shielded assets. We encourage you to check this tool out. It's an independent repository on GitHub, Zcash-dx-tool, and it contains a Docker that does the setup of everything, begins running Zebra, and then does a set of tests. Of course, you'll be able to go in and tweak the code and change the tests if you want to try other things out. So I'd like to see all of y'all play with it and see how it goes. So this is the one-slide summary of what we covered so far. We did zips, we did the circuit, and we looked at the various code repositories we've been modifying to bring ZSAs out to all of you. We have also begun the work for instantiating a testnet for ZSAs. First, we started local. We ran Zebra locally. We used the Zcash transaction tool that we just described. Then we moved to the cloud. We have run Zebra on an AWS ECS instance using Terraform to build the infrastructure. And we have also connected that with the Zcash transaction tool and run the test. So this is early stages. We have not tested this out with the ZSA features and with issuance and so on. We have, however, understood how to get everything running on the testnet. So that should be good for when we are ready to test the pieces all together. So where do we stand now? We have started talking to the Zcash ecosystem security lead, which is least authority, about doing an audit of the protocol as we get around to completing the last bits of the puzzle. There are also others like Geometry who had expressed availability to do an audit. So the more external eyes on our work, the better it bodes for security. And we are happy to support whichever audits are planned when they happen. We also have the fees portion that could benefit from some more discussion. As it stands, we have the same fee structure as in the proportional transfer fee mechanism. The prices are per byte. We'd love to hear more consensus on this part so that we can get this finalized as well. We are also in the process of streamlining the gadgets that are in the Halo 2 repository. This is for generating the zero knowledge proofs, the Halo 2. Like we mentioned earlier in the Orchard case, we are keeping abreast of the changes that are happening on all the repositories and making sure that our work builds correctly on top of latest versions. With that, we are now ready to move to asset swaps. But before that, we could probably take some questions if there are any. So yeah, I see there's a question, which is there a mechanism to preemptively set the maximum issuance when issuance begins? Or is issuance only terminated when the finalized flag is set? If it's the latter, what prevents an issuer from exceeding promised bounds by delaying final issuance?
So there is no mechanism to set a limit in advance, and only once the finalization flag been published to the blockchain, it is really finalized. I'm not sure that this is a real limitation, because if an issuer wants to guarantee some kind of some amount which is final, he can just issue the entire thing and keep finalize this asset and keep whatever is not immediately distributed in some kind of treasury. So the process is transparent, and we currently don't see it as a limitation.
Yeah, basically, since the issuance is transparent, it will be visible later. So it's not that, it's the reputation of the issuer that's on the line in that case. So the next question is, does the ZSA issuer have any way to track assets and transactions once owners have included the ZSAs in shielded transactions? It's basically no, because it's shielded. So we have the privacy just as in Zcash right now for ZEC. Does Gedit have plans to add functionality for issuance and transaction creation to the Zcash primitives transaction builder?
So everything is added as part of transaction V6. And of course, the builder structure remains the same as with Orchard. So you build V6 transactions, in the same way that you would build V5 transactions, just with a different set of parameters. So yeah, it's going to be part of the transaction builder.
Is the currently implemented functionality feature flagged in such a fashion that it can be merged prior to inclusion in a network upgrade?
So for Zebra, we did put the extra effort to include feature flags for the Zebra crate and for the Zebra code base. But for Orchard, it is currently not feature flagged because it is tightly coupled with the existing Orchard implementation. And I think to feature flag the Orchard/Orchard ZSA crate is a significant effort. I think we're going to review everything in one go, Orchard and Orchard ZSA together, and we are not going to feature flag Orchard. As with Zebra, yeah, it is feature flag.
So I think that's it for the questions for now. So we can continue on with the next part of our talk, which is asset swaps. So yeah, the main reason for Zcash shielded asset swaps is to enable any user to be able to exchange assets with other users in a peer-to-peer manner. That is, we want them to be able to perform these transactions without having to trust a third party or even the party they are swapping assets with. This allows for increasing decentralization over the network by reducing the need for trust in the users. The status of this effort is that so far we have prepared a new zip, which has been assigned number 228. This zip contains the specification of our design for the swaps protocol in the form of changes that are required over the ZSA protocol. We are looking forward to reviews and comments on this protocol so that we can get some external feedback while we move towards implementation. This will also reduce the chance of double effort that might occur if design changes are suggested after implementation is well underway. I'd like to now take some time to go over the main properties of our design, after which I'll go into the design a bit more at a high level. One of the key properties we are aiming for is for users to remain the owners of their asset until the swap occurs. Doing things like transferring the asset to some third party and so on requires additional levels of trust, and that could open vectors for attack, which we'd like to avoid. So instead, in our design, you own your assets until the point the completed swap transaction is on the blockchain, at which point it is a transaction that shows you sent your assets and received the assets you want. The protocol basically works by having someone take two pieces of a transaction that match and combine them together into a complete transaction and put that on the blockchain. The simple use case is that the party doing this matching is one of the two users itself. But our design is flexible enough to also allow it to be done by some third party or third party service. In either case, the protocol is secure and does not need any party to deposit their funds anywhere ahead of time, like we mentioned. The party that does the matching will know the values of the assets being swapped. The other nice thing of the protocol is that it builds on top of the ZSA protocol in a way that tries to maximize the use of the tools and security technology that has been developed for ZSAs and for Orchard. In fact, our design at present requires no new changes to be made to the circuit, which means no additions to proof size, proof generation, and proof verification times. We'll now dive a little bit more deeply into the design. There are two main pieces here, the swap order and the swap bundle. So when a party wants to swap some asset for some other asset, they create a swap order that contains the information of the trade they would like to perform. For example, someone may want to get 3 tokens of asset A by giving 2 tokens of asset B. That's represented in the top left figure in my pictorial description. Different parties will have different desired tokens that they are exchanging for other different tokens. These swap orders that these parties create do not go on the blockchain. They are communicated off-chain by external mechanisms. If you look at the orders, you will see that the person on the top left has an order that matches the order of the person at the bottom. Coincidentally, they also happen to be dressed as per the ZconV color scheme. So that's nice. These two swap orders can then be matched, which leads us to our next piece of the design, the swap bundle. The swap bundle is the result of the combination of two matching swap orders. It is this swap bundle that forms a complete transaction, which can then be added to the blockchain, and that completes the swap between the two parties. So we can now go under the hood a little bit, starting with the swap order. For the sake of ease of understanding, I want to simplify this a bit so that I can share the core of the idea without too much of the nitty-gritties. If people are interested in the nitty-gritties, I do encourage you to look at our specification in ZIP 228 and talk to us either during the conference or outside of it. We are always happy to discuss. I'd mentioned earlier that the swap order is where the party fills in the information regarding their side of the trade. So these are basically two pieces: the proposed input, which is what the party wants to send to someone who matches their order, and the desired output, which is what the party wants to receive at the end of the transaction. The pieces of information needed are the identifier of the specific asset and the value specifying how much of the asset is being exchanged for both of these pieces. For the specific exchange the party has in mind, that'll be the input will be 2 tokens of asset B and the output will be 3 tokens of asset A. Further, the swap order will contain the sum of the randomness of commitments from these pieces, which will be used for combining the orders later. So you can keep that in mind. The next part of the swap order is the relevant action group descriptions. These are similar to action descriptions that we have for transactions in Orchard, with some tweaks to allow for the possibilities of putting together actions that have different zero knowledge proof states or different commitment tree routes. I will show it as 2 actions over here. I've mentioned in the slide that they are incomplete actions. So the way you can think of this is that it is this particular party side of 2 Orchard ZSA actions, one to send 2 tokens of asset B and the other to receive 3 tokens of asset A. The design is such that when you combine it with the other party's swap order that matches, it will fill in the pieces to create complete actions to do both of these transfers. The swap order also contains authorization signatures so that it is clear it was issued by the appropriate party. And there is a new field added in this protocol, which is the time limit field. If there was no time limit, it would give the party performing the matching and posting on the blockchain what's basically a free option. That is, it would allow that party to wait indefinitely in the hopes of the exchange rate becoming more profitable for it, and then doing the swap in order to make some profit. Therefore, we have a time limit, which is expected to be a block number. Consensus will reject an action group that has a time limit that has already passed. So yeah, that was the simplified swap order overview. Next up is swap bundles, which is where we combine the swap orders. The swap bundle basically contains some header information. It contains the action groups from the specific swap orders that are being matched, and it has a binding signature. So when the swap orders are matched, the action groups from both these swap orders will exactly match their inputs and outputs. And this is what I'd hinted at earlier about the incomplete actions getting balanced during the matching process. I'd mentioned earlier about the commitment randomness being included in the swap order and it being useful for the matching process. So here's where it comes in. The binding signature needs to, as the name suggests, bind together all these different pieces in a way that it cannot be modified or cut and pasted in a different bundle. In normal Orchard, the transaction is created by a single party, so they know all the randomness and they use that to create the binding signature. Over here, though, we have randomness coming from two parties that needs to be combined in order to create the binding signature. We do this by providing the sum of the randomness of each party in their swap order and putting those values together to create the binding signature that we need. So yeah, if you look at the specification, you will see that the swap bundle structure actually looks like this. So I have highly simplified it to try and go to just the core of what is going on. A lot of the detail of why action groups are created and why they are needed and so on are explained in a lot more detail in the zip 228 and the rationale parts of that zip. We'd absolutely love for you to go over the spec and see what you think about it. So yeah, the great part about this design, as we said, is that it doesn't need any changes to the ZSA circuit. We will need to generate one proof per action group. So there will be multiple proofs in each swap bundle. There seem to be ways to aggregate Halo 2 proofs together. And so this is something that would be something good to do in the future. So this covers the updates that we were keen on giving from Kedit today. So thank you all so much for tuning in. And I think we have more time available for questions now. So yeah, so the question is, do you have any recommendations for how swap coordination can be implemented such that the coordination itself does not involve a central party? If a central party is required, are there potential legal ramifications for that coordination action that would deter coordinators?
So indeed, for the swap mechanism to work, someone need to aggregate the orders and then find the matching orders, match them, and submit them to the blockchain. So the simplest way to do it is to have a central party or multiple central parties that will receive orders from potential users, aggregate them and publish them to the blockchain. This is the simplest way. About the subject of decentralizing the matching process. So the first idea comes to mind is to create a decentralized network of matchers. So it's like a different network with a different set of incentives built on top of the existing Zcash tools and utilities. It is decentralized and incentivized separately from the Zcash network. This is the first thing that I can think of. The second thing is to go even further and to embed this functionality into the Zcash node. If the Zcash node is also includes software to match potential swap orders, basically we can provide software that anyone can be the matcher and to earn fees as a result. But again, this comes with the price of an extra maintenance and extra effort on the Zcash side. These are just ideas, but these are the things that come to mind about decentralized matching.
So another question is, how do you think Zcash can attract more developers from other blockchain projects to collaborate and make alliances to push Zcash further, like NIM, Brave, etc.? So I think the major plus point of Zcash is that it has these strong privacy and security features. And since it has all these, it's like the original privacy coin in a sense. So a lot of these projects might be looking for things that enhance privacy, and highlighting that would be one way to draw interest. Probably more outreach, more networking at conferences, having grant projects available to do things like building bridges to these different networks. Those could open doors to more collaboration. And yeah, I don't know if any other points, Pablo?
So it's not really a technical question, but at least from the ZSA perspective, the ZSA does provide the tools to basically bridge any other asset from any other chain into the Zcash blockchain, which by itself would open a significant amount of opportunities for collaboration. This is from the technical perspective. Although currently to bridge an asset, a trusted bridge operator is required.
Yeah, I think a lot of the impetus would come also from the community, in that like when there's demand for things from the community, there's more chance of grants being sanctioned and more chance of other people, like people from other blockchains realizing that that's a good idea to do. So yeah, we'd love to hear more about people using ZSAs for all sorts of things once they get deployed. So one more question, is there anything that the Zcash Foundation and or the Electric Coin Company could do to support this work that isn't currently being done?
So the answer is no. We are in tight cooperation and coordination with both Zcash Foundation, technical teams, and ECC. I expect as we move closer to this project integration step, this collaboration will be even tighter, and we will have much more interaction with both of these excellent teams.
I think that's all the questions that were in the chat. So thank you all once again for listening in, and see you around Zcon.
Okay, we are live. Hello, everybody. Good morning from the United States mountain area. My name is Bryan Gillespie. I'm a research cryptographer at Inversed Tech, a new cryptography consulting group. I'll be co-presenting with Ying Tong Lai from Geometry Research about a research project that we've done in collaboration with Daniel Benarock, who's my boss at Inverse Tech and CEO, as well as Andrew Miller at UIUC. Shout out to the Zcash AV Club for doing a great job on the presentation for this conference. It's been going really well. Been loving watching some of these talks. We're going to be talking about a research project based on a grant from the Zcash Foundation about programmable privacy. So this is a systematization of knowledge project, trying to understand kind of the state of the art on programmable privacy throughout protocols that are being developed and researched kind of at the cutting edge of the idea space right now. So our goal here is to survey and systematize blockchain privacy solutions, kind of focusing at the operational level. There's a lot of variations and technical details that go into making any privacy solution, as Zcash community members know. But our goal is to try and identify the big building blocks that go into producing privacy solutions of these sorts. So in particular, we wanted to kind of understand the big picture of how these privacy techniques come together, and also to assess the suitability of kind of these various solutions for how they might be used in the Zcash protocol or the ecosystem more generally. In more detail, we're looking at surveying a large collection of contemporary, trustless, distributed privacy protocols, and identifying the ways that they support privacy in their implementation. And in particular, how they provide some generic notions of programmability while allowing privacy in the execution of these application designs. We were aiming to define a framework for analyzing protocols and categorizing these privacy techniques in a kind of generic way that can be compared between protocols in some nice way. We wanted to identify architectures and features which work well together, kind of having a global bird's eye view of these architectures gives a good opportunity to try and think how the pieces fit together and what benefits of various techniques can be synergistic. And finally, we decided we wanted to formulate recommendations for the Zcash protocol for community development based on what we found. So what did we find? Well, okay, first of all, here's a list of privacy protocols that we reviewed in various levels of detail at various times in our study. This is a fairly long list, but fairly unstructured as described here. We'll talk a little bit more about how this can be organized based on our framework a little bit. But the bottom line is that there's kind of a wide variety of different types of protocols that we took a look at, including protocols that are under development and design and on the way to productization, some that are just prototype implementations of interesting ideas, and some of which are just architectures described in the research setting. Our emphasis when designing our framework was to accommodate the design developments that are on the more practical implementation side of things. So the protocols that are actually putting together solutions right now, as a way to emphasize solutions that show promise for being kind of concretely applicable in the near term for new designs. But we tried to consider a wide variety of sources for these techniques that are being used for programmable privacy. So the first thing that we noticed as we were doing our study was that there's a really common architecture that the Zcash community will be very familiar with, which is this notion of off-chain plus on-chain computation. Okay, it's exactly what Zcash uses as its basis for shielded pools. And it involves two phases of computation, what we call the independent computation and the global computation phases, which roughly take place off-chain in the client software privately, and then on-chain in the validator set. So at the start, the client does off-chain computation over wholly owned private data. So this is your Zcash notes are computed on, and some logic is checked to generate output notes of a shielded transaction. Private data that needs to be part of the application state is witnessed on-chain via commitments in a Merkle tree. Data and computations are confirmed by use of ZK snark proofs for correctness. And finally, once all of that is packaged together and the relevant proofs are transmitted to the network, then validators do some on-chain computation based on what's submitted, which can be as minimal as updating a nullifier set and updating the commitments, but can be more complicated in a more full-fledged programmability architecture. So the pros of this architecture and what makes it very widespread in solutions that are currently being deployed out there are excellent privacy properties. So the privacy of this independent computation phase only depends on the individual security of the client node that is doing the computations, and has nothing to do with the network overall. And additionally, because of the way that ZK snark proofs have been advancing over the last number of years, there's a lot of programmatic flexibility. Snark proofs are just exploding in usefulness in terms of their efficiency and in terms of the tooling available for them. So application development is just becoming easier and easier. I like to think of this as kind of the ZK thesis architecture that became popular a few years ago, and it still is rolling onward, and a lot of awesome solutions out there being developed. Some of the cons of this architecture, as also have been observed in various settings in the Zcash ecosystem, state bloat. So this architecture of using Merkle trees to represent commitments is very good for privacy, but the problem is that you can't tell which notes have been spent. That's kind of the point. And so you don't know which notes can be pruned from a state tree, and you just have to keep track of all of them in the naive implementation. And likewise, trial decryption is an issue that Zcash has grappled with, where if you want to find encrypted notes that have been addressed to you and you don't have any other signaling method to learn which notes are for you, then you just have to check whether you can decrypt every single shielded note that's submitted to the network that gets generated. And so this linear scaling with the throughput of the network is not great for especially light clients. These two cons in particular have growing issues if you increase the scope of this privacy mechanism to general programmability, because more applications means there's more state commitments and more encrypted data to trial decrypt. And so it's an ongoing question, like what the best ways are to address these issues in terms of performance. The last con on this list is what I think is one of our most interesting realizations from this study, and which we'll discuss in more detail as we go, is the notion that this private computation phase, this off-chain computation, is really intrinsically single party. And what that means is that when you're constructing ZK snark proofs, one of the basic ideas for kind of the standard snark proof constructions is that you need to know all of the details of the computation witness. And that means all of the inputs and all of the intermediate computations have to be known by the prover who's generating this snark proof. And that means that there's only one privacy regime for the prover, which is they see everything. And so if you're working over data that's fundamentally your own private data, then that's great, because there's no problem with you seeing all of that data. But if you want to try and use the private information from multiple parties in one of these computations, you run into trouble. Like, this is not what ZK snarks are designed for in their basic form. So looking at protocols that are using this, this kind of ZK thesis architecture of off-chain and on-chain computation, what we noticed is that there's a pretty wide variety of trade-offs that can be made in the design space. Our observation is that really the baseline for providing kind of the fundamental tools to support privacy-preserving applications on a protocol are fairly low. All you really need is a generic support for a verifiable computation engine, so some generic ZK snarks, as well as the ability to represent Merkle roots. And once you have those two pieces, that's enough to really support privacy-preserving applications for a sufficiently motivated developer. Okay, and this last point, I think, is a really fundamental issue. And the question is, what degree of built-in support should a protocol provide for various aspects of development that are involved in private privacy-preserving applications? And so we found a few axes that show some significant variation in these designs. One is the degree of permissionless application programmability that is even provided by the protocol. And the question that you have to ask is, well, if you're allowing anybody to permissionlessly deploy an application on the protocol, what are the standards of quality and user experience that are provided by those applications, right? There could be scams deployed on the network. There could be poorly vetted protocols in terms of security. But opening up application design to a broader community also enriches the overall space of products that are available. So there's a real trade-off as far as what the user experience is that a protocol wants to provide to users, kind of what the baseline guarantees on security of applications that are deployed are. Beyond this basic question of how much programmability is provided for, the other question that really shows some variation is how many resources in terms of compute are provided by the validator set, both in terms of computation, so how much of a full-fledged virtual machine is provided for on-chain computation, as opposed to just specialized specific computations like updates of account data or some restricted computational model, and especially on-chain data storage, which of course is an issue for all blockchains that are providing some generic computation. How do you handle both allocating and charging for the service of data storage on the network? A few protocols that kind of exemplify these variations in the design space here. The Aztec is developing an Aztec protocol, which is aiming to really be a full-fledged programmability layer. Think Ethereum, but with off-chain computation built in. And so they provide a nice domain-specific language, the Noir language, which gives a very nice developer interface for private programmability applications, as well as providing a full virtual machine and on-chain storage for data. So kind of they're aiming to be the full one-stop shop for private applications. Another example is the Mina ZK apps protocol, which is currently deployed in testnets, I believe, for Mina. And they are taking the opposite stance on how much on-chain compute to provide to applications. In particular, they are kind of taking the paradigm of off-chain maximalism to its natural conclusion. Applications have a constant fixed number of data slots available to them, which I believe when I was looking at the docs is 8. So you have eight places to put data for a particular application contract. So if you only need up to 8 pieces of data for your application, then great. Otherwise, those should probably represent Merkle state roots of some sort that can then be referenced from the private programmability logic and off-chain computation. So kind of two extremes of the axes of on-chain compute provided by a validator set. And finally, last example protocol that kind of is, I would say, closest to Zcash in their basic design and philosophy is the Penumbra protocol, which provides not generic programmability, but some decentralized finance applications specifically designed by the protocol without providing a generic programmability layer for application developers. And so they just take the stance of providing specific applications at a high quality of security and privacy, while eschewing kind of generic availability of programmability to developers. Okay, so now we'd like to return to this question of off-chain versus on-chain computation and single-party versus multi-party computations. So there's a really interesting question here, which is, you would really like, in an ideal world, to have full computational ability over private inputs from multiple parties in a way that doesn't reveal the private inputs or the intermediate computations. And so the question is are there ways to accomplish this in a cryptographic way using good cryptographic tools with good security properties? The fact that I'm showing this slide suggests that there may in fact be such a thing. And in fact, we've seen many examples of this when we looked at various protocols that we studied. We're calling this this kind of intermediate mode of computation mediated computation. And the idea is that some types of cryptographic protocols or other nice designs allow parties that are involved as operators in the protocol to conduct these computations over private inputs, while providing fairly reasonable assurances that the privacy of the inputs is maintained even from the computational nodes. This mediated computation does in fact accomplish private computation over inputs from multiple parties. What we found is that in order to accomplish this, generally additional security assumptions had to be made. So this could be something like an honest majority assumption, or the security of particular hardware configuration. Generally, the designs mean that the security assumptions control the privacy of these computations, but not the correctness of the underlying applications, which is an important distinction to make. So usually the global computation phase, the kind of verification of ZK snark proofs and signatures and the like on the public network, are able to handle kind of correctness issues of applications. So kind of these higher security assumptions for mediated computations don't involve security assumptions on somebody being able to spend your coins or something like that. The main techniques that we've observed and most commonly deployed for implementing a mediated computation phase. First of all, trusted execution environments get a lot of runway here. TEEs, the kind of SGX is the most common architecture that you see out there, allow some assurances that the computations being done are correctly executed and done in a private way, as long as you trust the security of the hardware underlying the computations. Advanced cryptographic methods such as secure multi-party computation and fully homomorphic encryption provide a more cryptographically based method to achieve private computation over private inputs from multiple parties. Typically, these are where you end up with honest majority assumptions on the compute nodes. And so this is additional security assumptions for the privacy that you end up with. Finally, another technique that comes in various contexts to various degrees, just some notion of delegated trust, where perhaps a user decides that they are willing to trust one or more parties in the community if they know who they are, or they have a legal agreement with them, or the parties are known to have a good reputation. Then they can be trusted to act on the user's behalf and preserve their privacy. And these techniques are not isolated. Sometimes they can be combined in interesting ways as well. So this is kind of the picture of the landscape of what we've seen, and in the second half of the talk, Ying Tong will talk about some more specific examples of what we've seen here. One particular example, the reason why I wanted to bring up Penumbra in particular, is that Penumbra makes use of a very restricted mediated computation phase in one of their decentralized exchange features, which is they provide sealed bid batch swaps. So they have a functionality for a decentralized exchange with automated market makers, liquidity providers, and in particular to provide privacy to users making use of this decentralized exchange. They allow users to batch their swaps together. So over a period of a block or several blocks, the swap requests from various users are aggregated into a single overall swap, which just sums the inputs, assets all into a single data value, and then some threshold decryption scheme allows the validator set to see only the batched amounts of the swaps, which provides some amount of differential privacy to the user's inputs to the swap operation. And I think Ying Tong will give some more details about that shortly. So one last feature that we took some time to develop in formulating our framework for this privacy-preserving computation is an ideal functionality, which gives some more details on how these different pieces of computation might come together in this sequence of steps, from independent computation to a mediated computation that is multi-party, and then to the global computation. This is designed as an ideal functionality in the vein of the simulation paradigm of security. So a real protocol then takes a look at how their concrete protocol realizes this ideal functionality by essentially showing that the real protocol can look exactly like the ideal functionality with an extra simulator layer on top. But the ideal functionality provides basically some hooks for concrete protocols to specify what information is expected to be leaked by the operation of the protocol, what exactly the computation steps are in the mediated computation phase, and what the security assumptions are for the privacy preserved by the mediated computation phase, with the hope being that that protocols can fill in the blanks, fill in these hooks for the ideal functionality, and use that as a starting point for understanding how the protocol's security and privacy properties can be better understood. So next, Ying Tong is going to talk about some specific protocols that we've analyzed in terms of, in particular, this three-phase model of computation. Before we do that, we have a quick pause for any questions. Okay, I see one here. So it seems like having privacy of inputs for private zero knowledge is a fairly niche use case and more difficult to achieve due to the requirement for generic MPC. And can you explain why this feature factored heavily into the SOK? Privacy of inputs for private zero knowledge. What are the primary applications for privacy of inputs, and why are these applications important to design for? Ying Tong is going to get to this in just a little bit. One of the things that we ended up deciding to do to focus our analysis of protocols was actually to focus on a specific application, which is the limit order auction. And the idea of a limit order auction is that you have input assets of some various types that you would like to trade for other assets at some specified types of prices. And so the independent computation phase, kind of the off-chain computation, is just witnessing characteristics of the assets that you have. and kind of preserving the privacy of the assets, of course, is an important factor in any shielded asset pool. And just being able to represent the kind of existence of assets of a particular type in a way that doesn't reveal that those assets is like, that's the independent computation phase. That's what it's trying to accomplish. So the mediated computation phase is then what happens after that, when you have orders from multiple parties that need to be matched together in a nice way that produces an output that is transactions that are actually finally decided upon, that satisfies everybody's requirements in terms of price. And so the mediated computation phase is actually the component of the overall architecture that we think has the most interesting design space right now, in terms of just the variety of techniques that are available, that people are developing in order to accomplish this. And ZK kind of is like the underlying bedrock that is needed for this kind of you need ZK proofs in order to prove validity of computations at various phases throughout the protocol design. All right, and no other questions so far. With that, I think I will hand it off to Ying Tong.
Thank you. So after we established this three-phase computation model, independent, mediated, and global computation, it became very clear, as Bryan mentioned, that the differentiating factor that we could use to classify these privacy protocols was the mediated computation phase. And from the initial unstructured list that we started out with, there emerged a very natural structure when we just focused on the mediated computation phase. So over here, this is one of the tables that appears in our SOK, where we're looking at the protocols in terms of whether or not they provide full programmability or general purpose programmability versus a specialized functionality on one axis. And on the other axis, we're looking at the sort of guarantees that are underlying the privacy in the protocol. So what are the security assumptions that the protocol is making in order to guarantee a level of privacy? And as Bryan mentioned previously, these guarantees are not for correctness. So for example, in Penumbra, if a threshold of validators colluded to decrypt an individual swap, then they could do no more. In other words, they could not change the swap. They could not forge it. All they can do is leak it. So this axis on this vertical axis is making very clear the assumptions for privacy that are used in each of these protocols. So in the SOK, we decided to zero in on a specific motivating application, that of limit order auctions. And let me just sort of go through the most basic variant of this, which is the order book. So this diagram might look familiar if you were at the ZSA swap talk right before this. Basically, an order book allows users to submit orders for asset swaps. So the user inputs the asset that they are selling and also the asset that they expect to get out of the trade with the corresponding amounts. And then there's a matching process whereby complementary orders are matched up in order to form fulfilled orders. And these are also known as balanced transactions or balanced actions, which can then be submitted on chain. Now, why we chose the limit order auction as a motivating application is for two reasons. The first is really just to limit the scope of the study with the huge range of protocols and the huge range of applications. It can get quickly intractable to survey the space. And we think limit order auctions are of interest to almost everyone in DeFi. And then secondly, limit order auctions are sort of the minimal example that still captures the interaction that is interesting in mediated computation. So namely, the fact that there has to be a computation done over private inputs from different parties. And furthermore, that the result of this computation has to be atomic. Focusing on limit order auctions allowed us to both limit the scope of the study, but also zoom in on the actual interesting part of the mediated computation. Another variant of limit order auctions is the constant function market maker, and this is very popular on public blockchains such as Ethereum. This is also what Penumbra allows us to do. So what's changed from the order book example is that the amount of the output is not specified by the user. But in other words, the price is not specified by the user. And in fact, the price is determined algorithmically and publicly by what's available in the liquidity pools. So what in the CFMM case, because the price is public, by monitoring the price changes, we can trivially reverse engineer what the order was. And this is very important to keep in mind when we go over some of the protocols later on. So the best we can do in the case of CFMMs is anonymity, unless we introduce batch auctions. So we'll see later on how that's done. So you saw just now the ideal functionality for the 3-epoch model, computation model. In our study, we wrote up 4 exemplary protocols in depth. So ZSA swap, Renegade Vice, Secret Swap, and Penumbra were found to be the representative examples for each of the classes of protocols. And they had implementations or proposed implementations for limit order auctions. So we wrote up UC style definitions for each of these. And we won't go through them in detail, but let's go through them at a high level, just to show you the amount of variance in the design space, even after we limit the application to just limit order auctions. So ZSA Swap and Renegade Fi here, they both implement order books, and Secret Swap and Penumbra both implement CFMMs. Now, I want to talk about the high-level takeaways first, the punchline, and then we'll go into each of these examples. And so that'll be easy for you to map the examples back onto these high-level takeaways. So in looking through these examples, we saw that the fundamental trade-off was between security and expressivity. Maybe this is not a surprising observation. The scarce resource is always on-chain compute. And so if your mediated computation is fully in protocol, fully on-chain, that means all the nodes in the protocol are involved in it. And therefore, you have to be careful of the burden that you're placing on these nodes. Effectively, an in-protocol mediated computation is happening in a resource-constrained setting. For example, we'll see later that Penumbra makes its validators responsible for a threshold homomorphic for homomorphic addition on threshold homomorphic encrypted ciphertext. And this is a very simple computation. If Penumbra wanted, say, to generalize this beyond addition to FHE, that would place more burden on its validators. Maybe it would need to have fewer validators, very likely. Another example is Renegade Phi. We'll see later that the Renegade Phi protocol consists of multiple two-party computations. And right now, the two PCs are doing a very specific matching algorithm. Once again, if they were to generalize this to some like general purpose virtual machine, that would be way more expensive to PCs, and they probably have to run this less frequently. Now, yeah, so if we don't want to pay the cost of in-protocol mediated computation, we could opt for extra protocol, which is cheaper. But now you're outsourcing the privacy guarantees to the application designers. So the privacy guarantees are no longer the same as your network security guarantees. Instead, it's equivalent to sort of instantiating your own 2PC or your own validators outside of the protocol just for your application. And furthermore, the extra nuance comes in when interacting with the anonymity set of L1. So we need to be very careful about preserving a unified anonymity set. And yeah, naively, if we fragmented the state of the node commitments into like siloed rollups, then that would, yeah, just reduce each application to its own anonymity set. Yeah. So the high level observation is also not surprising. Whenever there's a trade-off, a decision must be made, and the decision here absolutely must be informed by the application. So which invariants are necessary for your application? So in an order book, we want, for example, price efficiency. In the CFMM, we want front-running prevention. And there's this tension between optimizing for a single application and its invariants versus enabling general applications. And we'll have more thoughts on this in the conclusion, but I think it's a valuable exercise to build some intuition by going through some actual protocols. So now, yeah, our first two examples would be ZSA swap and Renegade Phi, which are both order books. So ZSA swap we just saw in Cadet's talk, but to quickly go over it again. In the independent computation phase, it looks very much like a normal Zcash transaction in which you're just spending a note. In the mediated computation phase, you're specifying sort of the intended outcome of your trade, the ZSA swap action. And as was mentioned in the previous talk, this matching of orders is extra protocol. and it's unspecified in the ZSA swaps protocol. So now, as mentioned previously, whoever's doing the matching must see the details of your order. So this could be a centralized operator. So I want to mention here also that if we wanted to bake it in to the protocol, for example, make it the responsibility of all the nodes to do this matching, then yeah, we would be revealing this order information at the protocol level. So this mediated computation that's currently extra protocol produces balanced transactions, balanced swaps that are then submitted to the blockchain and settled as in a normal Zcash transaction. So Renegade Fi looks very similar in structure. What's different is that the mediated computation here is done by a 2PC matching. So basically there's this handshake protocol, there's this privacy preserving two-party computation that produces a match if the orders are complementary and does not reveal any information otherwise. These two parties also collaborate in producing a snark proof that they did a computation correctly. So yeah, the point here is that people who opt into Renegade Fi are opting into this gossip protocol, this handshake protocol, this 2PC and collaborative snark. And this collaborative snark is verified then in the global computation. So this 2PC matching is very much baked into the protocol for Renegade Fi. But notice here that the independent computation and global computation still look pretty similar to Zcash. So Renegade Fi under the hood, they do use the commit nullify architecture that Zcash does. And what's changed in the global computation is that they're verifying more proofs like collaborative snarks. They're verifying like yeah, a bunch of bespoke proofs similar to how ZSAs would introduce more proofs, or it would alter the relation that the network is verifying. Now, the next two examples are CFMMs, and once again, they'll be very similar in shape. So secret network runs on a network of trusted execution enclaves. And how you would do how you would do a limit order auction there is you would encrypt your trade to the TEE's secret key. To the TEE, and inside the TEE, they will execute your encrypted trade. So inside the TEE, they'll decrypt your encrypted trade and execute it. So it's important to note here that the liquidity pools are still public. And so after the execution, the result is updated in a global computation and can only be decrypted by whoever owns the outputs of the trade. So what's important to note here is that this change in price after the trade is public. And therefore, if your transaction was the only transaction in the block, then just by observing the change in price, I can recover the details of your order. And that is actually a similar story as Penumbra. So Penumbra is also doing a CFMM style limit order auction. So over here, instead of encrypting to a TEE, you're encrypting to a threshold of the number of validators. And these validators are economically staked. So as mentioned before, this is deploying the network's economic guarantees for the purpose of this specific computation. And for the purpose of preserving privacy in this computation. And here, if a threshold of validators colluded to decrypt your swap, then they could front run, but they couldn't change your swap. So the mediated computation phase that all the validators participate in consists of a very simple homomorphic addition that's done over the ciphertext. So the point here is that we're batching all the orders for the same pair into a batch order. And so your privacy is as good as the size of the batch. And once again, if you're the only order in your batch, then will be very obvious from the price changes to recover your order. So the batch swap is decrypted by a threshold of validators and then publicly executed against the liquidity pool. And then later on, individual users can claim pro rata their share of the output by proving the inclusion of their original order in some block. So recommendations for Zcash. I think, Bryan, should I hand it over to you here?
Sure, I'd be happy to chat about this a little bit. Yeah, so in the direction of recommendations based on what we've studied for the Zcash community, the first observation from a lot of these protocols is that really only very limited kind of L1 consensus changes are needed to support generic ZK snarks and flexible data commitments that are needed for a programmable privacy development environment. Just making a more generic snark verifier and perhaps verification for certain types of signatures are basically all that you need in order to provide just the bare minimum baseline for programmable privacy on the network. The commit nullify privacy still remains state of the art for off-chain, on-chain computation. And there's really a question about what the best trade-offs are for Zcash in particular, in terms of what degree of programmability and what on-chain resources to dedicate to generic programmability. For the question of on-chain data storage, we think that it is probably worth considering mechanisms to support time-limited or metered storage. This is its own research question, of course, but it is an important consideration when you're considering increasing the surface area of on-chain data storage. To support a good developer experience, it is definitely worthwhile to provide a domain-specific language and high-level tooling of some sort for private computation. There are pre-built options available from various places in the ecosystem and other infrastructure. Obviously, Zcash has its own infrastructure for snarks and developer tooling, but focusing on the development of a DSL that has the ability to round off the sharp edges of any underlying cryptography that are involved seems to be a common theme for programmable chains, and seems to be important to kind of hide the complexity of the cryptography that's needed to implement these in practice. And finally, we think that including some kind of first-class support for mediated computation is important in development going forward. In particular, many protocols out there are integrating some kind of mediated computation layer in order to support private computation for multiple parties' private inputs. And especially in DeFi applications, this seems to be a very important consideration. We think that secure multi-party computation based mediated computation layers show a lot of promise and seem to be underexplored as a mechanism for generic programmability in a privacy-preserving way. The tools for MPC have been advancing in terms of their flexibility and efficiency over the last number of years, and we think that there's some really good potential to devise an MPC-based mediated computation layer that could be very performant and usable. This is another question for the Zcash community. How much of this infrastructure does Zcash, the Zcash Foundation and the kind of core software want to provide for users or for developers, as opposed to leaving that to developers to implement on their own? And this is a discussion that is important to have amongst a variety of stakeholders in this community. So that's the picture for our broad recommendations. Ying Tong, if you can click this forward. So two things that we're going to be putting out there sometime in the next several weeks. First of all, we're putting together a blog post with some more detailed recommendations that'll be going on the Zcash community forum as a starting point for continuing discussions. And we hope that you'll be able to join us in talking about these questions. There's a lot to discuss and a lot of both high-level considerations and technical details that go into it. We'll also be putting a preprint of our SOK paper out on the ePrint archive. And so keep an eye out for that, and you can see more about the detailed analysis of these protocols. And we hope that you can help join us for the continuing discussion about what the right path forward is for implementing some type of programmability in the Zcash ecosystem. And also interesting research questions regarding how these designs might be implemented for Zcash's architecture and in a very high standard of security. So, and I think that's it. So thank you. And we'd be happy to answer any questions if there are further questions. Okay, we have a question here. How does shielded programmability intersect with plain programmability in terms of software engineering? And what are the research areas that you envision that will need to be explored to make shielded programmability possible?
I
Yeah.
think in the context of Zcash, especially, like the strength of the Zcash protocol is its huge anonymity set, and it is not trivial to preserve this anonymity set across multiple applications. So yeah, I think this is one sort of design difficulty in shielded programmability that we don't have in plain programmability. This tension between wanting full expressivity for your application versus wanting to still be part of the anonymity set and to be able to compose with other applications. I think the compromise that Aztec made is that they allow for public calls. So like cross-application calls can be public because otherwise I think only a very limited class of applications would be viable if all applications had to compose fully privately. But I think this is definitely very important design question, like how do we introduce programmability on Zcash without fragmenting the anonymity set, while still allowing for interesting applications with meaningful composability.
And I do feel that the design of a domain-specific language for implementing these private programmability applications is like deeply connected with these questions of what the computation model is under the hood. So looking at other projects that have developed DSLs that are designed to abstract away these questions is like a really good starting point. So Aztec's Noir language and Mina ZK apps have their snarky JS. I think it's called O1 JS now. But I do feel finding inspiration in these projects that have taken some time to understand the kind of synthesis of off-chain and on-chain computation and abstract that is a good place to start.
And personally, I think ZSA swaps is a very good motivating application to start like larger discussions about programmability. So I think ZSA swaps, the previous speakers had proposed, further changes to the relation to capture like the atomicity of the swap, etc. Yeah, so a different approach would be to just allow for like a separate ZSA swap application to be uploaded, and then nodes could be spent like according to that applications. This basically alio exactly, but doing so in a way that doesn't shrink the anonymity set of the ZSA swap users. So yeah, I think ZSA swaps would be a great starting application that motivates like the future of programmability on Zcash.
All right, we have looks like one more question, which is probably the last we'll have time for, which is what do you consider the important features of a programming language or DSLs for generalized shielded programmability?
I think for me, top priority is safety. So we said just now that the moving the privacy guarantees extra protocol places the burden on the application developers. And for example, in MPC, it's not the case that every MPC circuit guarantees non-disclosure. Over like a set of data, you could write like a trivially disclosing MPC computation. And that is also true for like, even if you use ZK snarks, you could still like trivially de-anonymize or like just violate a lot of the invariants that a user might have been taking for granted. So a user or an application writer. So I think having a DSL that it's kind of like how Rust keeps us safe from like accessing memory that we shouldn't. So writing a DSL that very strongly guides the user away from de-anonymizing or like disclosing patterns. I think that would be like the number one feature I want.
Alrighty, and I think that is all the time we have for our session today. So thank you again for the opportunity to speak today. I guess we'll
thank
be on.
you, and thank
Thanks so
you,
much.
Audiovisual Club.
Yeah, absolutely. This has been very well run as a conference.
Ele ligou assim, não faz isso, não pode ligar.
Fala, Pedrinho, beleza? Tudo bem, irmão? Me diz uma coisa. Ó, o computador, quando ele ligou, ele ficou assim, ó. Agora nada acontece. Nem desligar eu consigo. Ele fica rodando essa bolinha aí, não liga e nem desliga. O que tu acha que é? Não sei, a Marissa, eu vou perguntar.
And one, the mining uses. Welcome everyone joining virtually, or well, I guess you're all joining virtually, even if you're in person somewhere. There's a network link in between. But I'm Christopher. I work on Anoma and Nomada at Helix. A long time ago, I also wrote a Zcash block explorer. So I've been interested in Zcash for a long time, since it launched. This presentation is called To Bridge or Not to Bridge, misquoting Shakespeare, What's at Stake? And in it, I am going to attempt to do a few things, and I am not going to attempt to do a few other things. So just to describe those briefly, this presentation is sort of what I thought would be hopefully a useful elucidation of options and trade-offs related to Zcash, proof of stake, and interoperability, which are very related topics. And later on in the presentation, I'll talk about why I think they're related topics at a moderate level of detail. So this is more detailed than like to do proof of stake versus proof of work. That's not a very detailed question. This is a more detailed look at sort of what options and choices exist within proof of stake and interoperability, but it's not at the level of detail of a protocol specification. So it's sort of a mid-level of detail, and it's particularly focused on choices, which I think Zcashers kind of are still considering, as they and you consider potential possible futures involving proof of stake and interoperability. So this presentation is not an argument that Zcash should or shouldn't do X for any X. I'm just trying to clarify what the sort of options and trade-offs are, such that if you want specific features from the user perspective, hopefully this presentation will help you understand what kind of design choices at the proof of stake or interoperability protocol level impact those kinds of features and those kinds of, later on in the presentation, I'll get into some of the considerations for proof of stake or economic or even almost political, and I'll get into what some of those might look like. Cool. So first, I want to offer a little background just on what I mean by these terms. So proof of stake is, it's a big umbrella word, and it can mean a lot of things. And one, the original usage of the term was kind of proof of stake as contrast to proof of work. So where proof of work uses mining, uses repeated hash calculations, at least in the original formulation, to vote for particular, in some sense it actually is a voting mechanism by hashing on a chain, you're voting for it, but to vote for particular chains, and then a fork choice rule, typically, which takes the longest chain, sometimes with some additional constraints, longest chain according to work. Proof of stake was a kind of different fork choice rule, which would take some kind of votes from stake directly, where stake is typically understood as relating to a token. So tokens are typically locked, and that becomes something called stake, and stake can be used to vote on particular chains or versions of history, and then there's some algorithm to determine which chain is chosen. And that algorithm is the fork choice algorithm, or finality. To distinguish between those two, fork choice is a property of Nakamoto consensus algorithms, where you have multiple valid chain forks, you want to pick one of them, and finality is sort of the algorithm that you use to determine whether a particular block is final, as in whether you believe that it will never be reverted. Now, in Nakamoto consensus, like in Bitcoin and in the current proof of work version of Zcash, there is no finality, as in sometimes it's called probabilistic finality, or there's only a kind of probabilistic argument as to why a particular block will never be reverted. But with the longest chain rule, Zcash might have, in the default client, there might be a rule to reject chains that are just too old by timestamp, I forget. But with a basic longest chain rule, there could always be a longer fork that you just don't know about. So for that reason, you don't have finality. And fork choice and finality are very coupled. I would consider them one kind of component of proof of stake. But the other component of proof of stake, and the component which has kind of, flourished in a lot of different designs in recent years, is what I call the staking and rewards mechanism. And the staking and rewards mechanism is the part of the state machine which determines how voting power is allocated to public keys. So ultimately, in consensus, in some kind of BFT consensus, where you're sending around votes, the votes are signed messages, they're signed by public keys, and the votes have some kind of voting power associated with them. And voting power is not just as simple as tokens, right? So if you have some tokens, those will correspond to voting power in some way, but often the way is a bit more intricate than just like one token equals one voting power. For example, you might need to lock the tokens first in delegations or bonds. You might need to register as a validator. There might be limitations on how that gets accomplished. It's even possible, although rare, I think, but it's possible to use different rates for allocating voting power to tokens. There's a lot of design choice. Well, there are a lot of design choices and just a lot of design space there. And the rewards mechanism determines how the rewards, so whatever kind of portion of inflation and fees is dedicated for proof of stake, are paid to validators and delegators if the system supports delegation. And many of the questions of how you should pay rewards are kind of economic or crypto economic questions, and they don't necessarily have clear objective answers. So later on in the presentation, I'll talk a little bit about those. But I want to distinguish or kind of split proof of stake into these two main components, particularly because so far I think Zcash is focused mostly on fork choice and finality, both because Zcash was historically proof of work and because so far, at least the research that I've read into proof of stake within the Zcash ecosystem has really been focused on that component. And that component is important. It's critical, it's required if you want to move to proof of stake, but it's also not the whole picture. And it's, I would even say, like, maybe only half the work. So for that reason, I will focus most of this presentation on the second component with regards to proof of stake. Now, to give a little bit of background on interoperability, by interoperability, I mean potentially different things, but at minimum, the ability to move ZEC or Zcash to and from other chains in a decentralized fashion. So I include decentralized fashion because technically you could already do a kind of interoperability with some single central entity. Like if I decide to issue an ERC20 token and I call it ERC Zcash, and I promise to give you one Zcash if you send me one ERC Zcash, then in some sense, I've created an interoperability protocol between Ethereum and Zcash, but for good reason, you might not trust that kind of protocol because you have to trust specifically me. So I'm going to talk about more centralized methods of interoperability. Now, depending on what Zcash also does in the future, interoperability is something that really happens at the chain level. So once you have interoperability between Zcash and other blockchains, you could probably easily add interoperability for other things happening on Zcash and the other blockchains. For example, if Zcash adds support for ZSAs, Zcash shielded assets in the future, which I understand Kedit is working on, then ZSAs could easily be moved back and forth to other chains, with the same kind of basic interoperability as would support doing that with just SEC. If there are more complex, programmable ZSAs or other kinds of more complex applications on Zcash, those could also use, pass messages to and from other chains, which aren't just tokens. So that's what I mean by interoperability. Now, you might ask, why consider proof of stake and interoperability together in one function? The basic reason is that interoperability requires finality. In order for other chains to interact with your chain, they need to know when they can treat a particular block, and state transitions referenced in that block, including tokens, stuff like this, is final. Proof of stake, from the kind of consensus or fork choice finality perspective, provides a clear finality rule typically. It's also typically cheap to verify, whereas verifying proof of work, there's some more efficient like clients like Fly Client, but proof of stake is generally much more efficient to verify than proof of work because you just need to check some signatures. For this reason, proof of stake and interoperability are often very related, and if you look at the ecosystem of protocols out in the world, you'll notice that they tend to come in pairs, as in there tends to be a specific proof of stake design associated with a specific interoperability design. So in the Cosmos ecosystem, there's bonded proof of stake and the Cosmos SDK, which I'll talk a little bit more about later, and IBC. In Avalanche, there's staking and subnets. So these protocols are kind of related there. And I think it probably makes sense for Zcash. This is maybe the only normative statement in this presentation. I think Zcash should consider these aspects in tandem. It would be probably much more awkward to think about proof of stake and interoperability separately. That's, some other older projects have done that, like, Ethereum, for example, considered proof of stake and interoperability separately. And I think, all else remaining the same, that's probably made their life harder. So it would be easier for Zcash to consider these two aspects in tandem. So I just want to offer a kind of user-facing overview of what proof of stake will probably change from Zcash today. So one thing that will change is consensus security. In proof of work, of course, security is provided by miners. In proof of stake, security is provided by validators, or at least partially validators who are issuing the signatures. Now, in some hybrid designs, such as the trailing finality layer, which has been proposed by the Electric Coin Company, that's a hybrid design featuring both proof of work and proof of stake. So security is provided by both of these parties. For more details on how that works, I would refer you to the trailing finality layer book, or I believe that Dara is also giving a presentation at the ZCon about the topic. But in any case, consensus security will change in some fashion. The operator roles will change. So in a sort of gradual transition, mining will be gradually phased out, or in an immediate proof of stake transition, it would be phased out all in one go, like Ethereum did. Staking will become possible. Now, where mining is basically one role, like either you're mining or you're not, staking tends to contain at least two roles, those of validation and delegation. To summarize briefly, validation is signing blocks, publishing signatures. That requires an online node, tends to be more professionalized. You need to run a server that's on the network all the time, processing blocks, validating them, issuing signatures. And delegation is usually something which is much more kind of open to users who aren't online all the time and perhaps don't want to run nodes. And they can, using protocols which support delegation, they can lock up some of their stake, which in this case would presumably be ZEC, and basically delegate that stake to a validator who gains voting power kind of the user's stake. The user delegates it to the validator, and they gain the ability to vote on the user's behalf, or so to speak. Yes, there are kind of two roles typically in proof of stake protocols, whereas there's really only one in mining that has economic significance to the protocol. The other consideration for operators is that really mining and operating a validator are very different from a kind of security perspective, from a what you need to do perspective, from a business perspective. Slashing is possible in proof of stake when you run a validator. There are different kinds of distribution logic. So regardless of the specifics of the change, ZEC, newly issued ZEC, will no longer just go to miners. Some of it will have to go to the validators, and it might also go from the validators to delegators. So there will be some changes in how ZEC is distributed, and there are a lot of specific decisions to be made there. So I want to answer the same question from the perspective of interoperability. What will interoperability change from Zcash today? Well, at minimum, ZEC will be able to be sent to other chains as back. And on those other chains, ZEC could be used in other applications. For example, on Osmosis, which is a DEX in the Cosmos ecosystem, ZEC could be swapped to and from ETH, Atom, USDC, or any other asset on Osmosis. If there are stablecoin vaults, there are many of those in Cosmos, Ethereum, and other ecosystems. ZEC could be locked as collateral if someone is willing to accept it. The one thing which I think is cool is that ZEC could be held by DAOs on other chains, or by kind of other multi-signatures or other accounts who might wish to kind of hold it there because they have their custody set up there, or want to use it in different programmable ways, which are not possible to do on the Zcash chain. Now, if Zcash adds other features such as ZSAs, then these other features would probably gain similar benefits, as it would be possible to send ZSAs to other chains and back and use them in other applications. And if Zcash consensus and state machine history just in general can be verified on other chains, different developers could build applications which take advantage of that. For example, applications which do something if you send a transaction on Zcash, or applications which aggregate statistics from the Zcash chain over time, stuff like this. So now I want to dive in specifically into proof of stake. So as a refresher, earlier I talked about the two independent components of proof of stake. The first, oops, there's a slight typo there, but finality and the fork choice rule, and the second, staking and rewards mechanism. Now I want to talk about those in more detail in turn. So fork choice and finality. The fork choice and finality rules, as a refresher, determine when full nodes will consider a block final and which fork they might pick amongst a selection of valid chains. Now, I think so far the Zcash ecosystem has done the most research into this part of proof of stake. In particular, the Electric Coin Company has conducted a bunch of really awesome research into something they call the trailing finality layer, which provides both of these aspects initially as a hybrid proof of work and proof of stake protocol, with a planned eventual transition to pure proof of stake. The proposed protocol is described in quite sort of detailed language at this URL. And I believe the presentation will also be happening about that at CCon. Now, most of the details, at least the details which are specified in this book, are independent from the staking and rewards mechanism, as in these details assume that there's some public keys and they have voting power, which is chosen somehow. And then this book describes how you would implement the kind of consensus logic and fork choice finality rules given that allocation of voting power. But at least so far, there's not a lot of detail here as to how that voting power is actually allocated to public keys, how staking and delegation work, stuff like this. So I tried to kind of canvas the history of discourse in Zcash, and I'm sure that I've done so imperfectly. I can't read everything, but I tried to canvas the history of Zcash for stated preferences about the staking and rewards mechanism, because there are a lot of choices here. I found a few presentations which went into a little bit of detail, some by Nathan Wilcox at past CCOMs, discussing a kind of desire to support delegation. Not all proof-of-stake protocols support delegation. Some of them don't, or some of them do it out of protocols. This is a choice. You don't have to do it. And there's a desire for easy entry of new validators. And then the ECC's TFL book there's a section listing goals and non-goals, and a few of them are relevant, although they're kind of high level. One stated goal is that the protocol should enable users of shielded mobile wallets to delegate ZAC to POS consensus providers, and earn, i.e. validators, and earn a return on that ZAC coming via ZAC issuance or fees. Doing this may expose users to a risk of loss of delegated ZAC, such as through slashing. The protocol must guarantee that proof-of-stake consensus providers have no discretionary control over such delegated funds, including that they cannot steal those funds. So this implies in-protocol support for delegation as opposed to like out-of-protocol support. And some stated non-goals in that TFL book are in-protocol liquid staking derivatives. I'll talk a little bit more about what those are later. And maximizing the staked voter, or I think they mean validator count ceiling. So these are kind of what I understand as some articulated preferences in the Zcash community. I'm sure there are others. I'm also not entirely sure whether this goal is intended to refer specifically to shielded mobile wallets as opposed to other wallets. I'm going to assume that it's referring to just people who hold ZAC in general, but especially including users of shielded mobile wallets, as in it shouldn't require running a full node. But I assume that people who are running a full node should also be able to delegate. If I'm wrong about that, someone from ECC, please let me know. Okay, so in order to kind of provide some useful examples here, I thought it would be useful to talk about some staking and rewards subsystems or proof-of-stake subsystems which exist in the world and what is different about them and how those differences might be relevant to things which the Zcash community cares about. So there are a lot of examples. The good news about implementing proof-of-stake at this point in time is that many people have done versions of it in the world, and many of those versions have actually been deployed in practice and run for many years. So you can see not only the technical implications or like basic security implications, i.e. have these systems forked. That's like a very basic security implication. But you can also see the kind of some of the socio-political implications. And one thing about proof of stake that is quite different than proof of work and that I think is sort of important for the Zcash community to consider is that it really has very different socio-political structure. So in proof of work, the entities performing the role of kind of providing consensus security miners are anonymous. They don't care about maintaining a reputation because it has nothing to do with their returns. They just need to mine as efficiently as possible and as fast as possible. And they typically aren't necessarily very integrated into the community structure. They're often kind of solo mining operators. Sometimes they might want to be anonymous for reasons of preventing denial of service or reasons of legality. But also just there's no reason for them to participate in the community. They don't gain any material benefits from doing so, at least not as relates to running miners. And mining operations just tend to be competing on the basis of hardware, right? And proof of stake, however, validators, at least in systems where validators are competing for delegations, validators are really competing on the basis of reputation, which means that they often end up doing other things, as in they often end up building or operating wallets, building or operating additional software. Sometimes they host conferences. They often end up involved in the community in other ways because they are because they benefit from doing so, because doing so exposes their brand to users who might delegate. and kind of demonstrate some level of commitment to the project, which delegators often might take into consideration when they make decisions about who to delegate to. So one kind of thing that I encourage the Zcash community to do is to think about what kind of social structure you might want, particularly what kind of relationships between validators and delegators you might want, study existing ecosystems, both how they implement proof of stake and what kinds of these relationships have developed in those ecosystems, kind of use that data to make an informed decision for Zcash's design and community goals. And some of the specific decisions here, how many validators are there? How does the commission, how do things like commission work? How do rewards work? These really affect the socio-political structure because they affect, are validators competing or collaborating? Are there a lot of them or a few of them? Or they're sort of, how easy is it for individuals to run a validator versus are they almost always delegators? Are delegations often intermediated by things like liquid staking, etc.? So I'm going to cover 4 examples from other ecosystems here. I will cover Ethereum, the staking and rewards mechanism in Ethereum. I'll cover the staking and rewards mechanism in the Cosmos SDK used by most Cosmos chains. I'll cover the staking and rewards mechanism in Penumbra, at least according to the latest version of their protocol spec. And I'll cover the staking and rewards mechanism in Nomada, which is a project that I work on. There are a bunch of other examples that I think would be interesting that I won't cover here just due to lack of time. I think Avalanche, Tezos, Solana, and Polkadot all have kind of interesting and different proof of stake mechanisms and interesting and different, socio-political, community, and economic structures, and they're probably worth studying. First, I want to talk about Ethereum. So Ethereum implements a version. All of the other examples here use Tendermint. So Ethereum does not use Tendermint. Ethereum uses Casper. It implements a much different proof of stake, both a different fork choice and finality rule and a different staking and rewards mechanism. In particular, the kind of trade-off that Ethereum takes is that finality is slower, but they support many more validators, where only a subset of validators sign each block. These validators in Ethereum must lock at least 32 ETH. They have withdrawal logic, which is configurable with smart contracts. I believe that it's quadratic, but at least correlated slashing for faults, meaning that if multiple different validators commit faults that are discovered within a similar time frame, the slash rate increases. This is designed to kind of encourage decorrelation and some more decentralization. Now, at least recently, liquid staking or proof of stake derivatives have become very common in Ethereum, particularly Lido. These are implemented with smart contracts. And an important thing to understand as it relates to socio-political structure in the context of liquid staking is that liquid staking providers, they provide an important service for delegators. Part of that service is the access to a liquid token that you can do other things with. Part of that service is validator selection. So one thing in proof of stake protocols in the world, in kind of the world right now, that I would argue typically doesn't work very well in practice is that evaluating validators is difficult, right? In order to evaluate the security of the validator, in order to evaluate how much they contribute to the ecosystem, all of these other things that you might want to evaluate as a delegator, you need a lot of information and a lot of time. And you need like specialized knowledge of validator setups and how to tell good ones from bad ones. And you need a lot of knowledge of the community and ecosystem structure and what the validator is doing for, in this case, Zcash. And this is just like, this evaluation is very expensive. So it's hard for individual delegators, especially if they only have a small amount of ZEC and don't necessarily, it doesn't make sense to them to commit a lot of time to these kinds of discussions and research. They often don't really know who they should delegate to. And one service that liquid staking providers such as Lido provide is that they, because they're of course kind of central entities, they can spend a lot of time evaluating validators, quote unquote, on behalf of users of their liquid staking token. So I think this is something, something interesting for Zcash to consider is what you want your relationship to liquid staking to be. It's not necessarily entirely something which is only decided by Zcash, as in even if the protocol doesn't support it, like the Ethereum protocol doesn't support liquid staking, it just supports smart contracts. And lots of other parties, such as Lido, built liquid staking on top of that. Using smart contracts, Now, Zcash, the blockchain doesn't support smart contracts, but probably eventually Zcash will become interoperable with other chains, so people could build proof of liquid staking systems on other chains. Or even if that doesn't happen, people can use threshold cryptography and validator multisigs, and they can still build liquid staking systems. So it's probably impossible to stop. And I think that the more kind of salient question is just what kind of economic relationship do you want your protocol to have to it? And do you want it to happen sooner and within control of the protocol, or later and probably out of the control of the protocol? And in the Ethereum staking and reward system, just kind of relevant for implementation concerns, is implemented in Ethereum clients, which are available in lots of different languages. So now I'll talk about the staking and reward system in the Cosmos SDK. In the Cosmos SDK, Cosmos implements something called bonded proof of stake. So there are a few hundred validators, because all or most of those validators sign each block, and they all have to send messages to each other in Tendermint or comment. So the number must be relatively small. Because the number is small, and because they all or most sign each block, finality is very quick, measured in terms typically of seconds, like 5 seconds. Now you must typically, or in the Cosmos SDK, you must be in the top N, like 150, a few hundred validators by stake to be a validator. So most users cannot be a validator. They just don't have enough stake. Instead, however, they could delegate to validators. The Cosmos SDK supports instant redelegation. So if you don't like your current validator, you can choose a new one without waiting. Validators take some commission. I think the typical ranges right now are 5 to 10%, but the rest of the rewards go to the users who delegated to them. And in the Cosmos SDK, all of this commission and rewards logic, including rewards going back to the users, is protocol enforced. So to go back to kind of the goal here articulated by the TFL book, I believe this implementation or this design satisfies this goal, as in the validators in Cosmos do not have discretionary control over such delegated funds, and the protocol enforces that the users get the rewards that the validators earn less the commission. Now, the Cosmos SDK also does not implement liquid staking, but in the Cosmos ecosystem, liquid staking has been implemented by other chains, particularly one called Stride, using IBC. And the Cosmos SDK is implemented in Go. Another example I want to talk about is Penumbra. Penumbra also uses Tendermint, so there are a few hundred validators, all or most of which sign each block. Fast finality measured in seconds. You must be in the top end stake to be a validator. Same things there, because it's using Tendermint. Now, what Penumbra does that's quite different from the Cosmos SDK is that it implements native liquid staking. So in Penumbra, each validator has their own liquid staking token. These are tradable. They can be exchanged. When you delegate to a validator, you receive the LST, and you can send the LST back to the protocol, or so to speak, to undelegate it after a period of time. Now, these undelegations are rate limited in a queue. For full details there, see the Penumbra protocol spec, and this is implemented, as far as I know, in Rust. And the last example, now Penumbra is not live yet, so there's no ecosystem to study here. There's only an ecosystem to study for Ethereum and Cosmos. The last example I'll talk about here is Namada. Namada is also using Tendermint. It's not implemented in Go, it's implemented in Rust. The system is pretty similar to the one in the Cosmos SDK. There's delegation, there's bonding, instant redelegation, there's commission enforced by the protocol. But one difference is that Namada does cubic slashing, which is like quadratic slashing, but instead of quadratic, it's cubic. So there's even like less penalty for uncorrelated faults and more penalty for correlated faults. And Namada is also not yet live, but one thing which might be interesting to the Zcash community is that this is implemented in Rust, which is probably the language that Zcash would use, at least from what I understand from the current client implementations. Okay, so I've gone through some of the details here, just to kind of summarize some takeaways that I think might be important to consider with the Zcash ecosystem. One, the fork choice rule is only half the battle. I think there's a lot of discussion, that I see on the forums and in presentations on proof of work security versus proof of stake security. And that discussion is very important, but it's not sufficient in order to actually have a proof of stake system. You also need to figure out what you want for the staking and rewards mechanism. And I think This could be difficult because a lot of the decisions made in the staking and rewards mechanisms they're not really objective, or they're like, you can do very clear kind of discrete security analysis, the fork choice rules. There's a lot of that in the TFL book, but a lot of these decisions, made here in the staking and rewards mechanisms are kind of, they relate more to the socio-political structure. How do you want delegation to work? How do you want rewards to go around? Which entities are you willing to endow with some additional trust in the operation of the protocol? Which are you not? Do you want faster finality or more validators? I would understand these as like more, socio-political, socioeconomic questions. They're not just protocol security questions. Another takeaway, sometimes people say just use Tendermint, and I think that that's well-intentioned, but too simple in this case. All of these example systems would require substantial changes. Even if Zcash just like used Tendermint for the BFT consensus part, all of these example kind of staking and reward systems would require quite a bit of work in order to be used with the current Zcash state machine and code base. And it's not clear that any of them exactly satisfy the Zcash community's requirements. You might also just want to design your own and pick and choose pieces from these different mechanisms. And these finer details and choices really affect, decentralization and the distribution of power within the community. Validators care about reputation, as I mentioned, and you can probably mine these existing ecosystems for a bunch of valuable practical data on how proof of stake has affected their trajectories. Some choices to kind of take away that, I think are still to be made. How do you want delegation and rewards to work? Do you want the protocol to enforce reward distribution to delegators, or should validators do this on their own? How do you want slashing to work? Do you want liquid staking inside the protocol, outside of the protocol? If it's outside of the protocol, do you expect it to happen and you're just fine with that? Or do you want to try and prevent it? And how do you prevent it? That's very difficult because, as I mentioned before, there's kind of a real service being provided that a lot of delegators find to be valuable. Another question which I haven't seen discussed so much so far is who might the validators be in the Zcash ecosystem? I think many validators in Zcash might come from the existing ecosystem. It's not like miners are very mercenary. They switch from chain to chain in accordance with what's more profitable. They'll come to Zcash if Zcash is profitable with their hardware, and they'll leave. It's not. Whereas validators tend to be much more embedded in the long-term structure of a community. So I think it would be interesting to figure out who some of these validators might be and what kind of relationships with delegators they want and what relationships the delegators want. Okay, now I want to talk a little bit about interoperability. There are two main options. One, implement IBC in Zcash, and two, use a bespoke bridge, which would need to add Zcash support. So IBC is the interoperability protocol originally developed by Cosmos. It's now supported pretty much everywhere, or at least it will be by the time Zcash would implement it. The big advantage of IBC is that it really minimizes the trust assumptions required for interoperability. Implementations are available in Go and Rust. In order to implement IBC, Zcash must do basically two things. One, there needs to be an efficient light client, and two, Zcash needs to integrate IBC code into the state machine. The second option is a bespoke bridge. A bespoke bridge basically means that some other chain and validator set runs Zcash nodes, and the validators of that chain run a multi-signature account on the Zcash chain. So in this sort of bridge architecture, there are two sides. There's the Zcash side and there's the bridge side. Sending from Zcash to the bridge chain just entails sending Zec to the multi-sig on the Zcash side. Then the validators will confirm that send, and they'll mint some kind of Zec voucher on the bridge side. And to send back, you burn Zec vouchers on the bridge side, and then the validators will send a Zec from the multisig on the Zcash side to whatever address you specify. So we made a proposal for potentially doing this with Namada, which goes into this architecture into some more detail, and you can find that on the forums. So I want to talk about the trade-offs between these two options. The big advantage of IBC is that there are no additional trust assumptions beyond the chains involved. And once you've implemented IBC, it's inexpensive and quick from a user perspective, as in you can send very quickly from one chain to another, and you don't need to pay additional fees to some bridge operator. The disadvantage of IBC is that it might take a long time to implement. It's at least dependent on proof of stake, and depending on the details of proof of stake, especially like light client and state machine integration, it might require additional work. The bespoke bridge adds an additional trust assumption in the bridge operator set, at least for transfers. Beyond that bridge, if you're just transferring to the other chain, it's not an additional assumption. But if you want to transfer beyond, it is compared to IBC. The advantage of the bespoke bridge is that it could be much faster to implement because it's not dependent on proof of stake, although the bridge operators must pick some kind of finality rule. for when they determine a block to be final for the perspective of sending coins to the other side of the bridge. Now, Zcash could choose to do both. There could be a bespoke bridge now, and Zcash could switch to IBC later. In some sense, it's the best of both worlds, but it does require more work. Okay, what's next? I just want to talk a little bit about, kind of what we're working on and what kinds of collaborations we're looking for. One other thing, which is not relevant to the rest of the content of this presentation, but we as in Namada are working on shielded airdrop to Zec. There's a technical thread with some of the details that I've linked there. If you have sort of technical feedback, we'd love to hear back from you. We just heard back from the ECC yesterday. Thank you, everyone at the ECC, for a really comprehensive response, and we're working on now understanding and responding to that. We'd also love to hear from other people who have technical thoughts. And there's a separate thread for kind of non-technical thoughts. We are very open to developing a bespoke bridge on Namada, and we're also open to offering grants and assistance to someone who wants to do this. We are also open to supporting a proof of stake and IBC implementation on Zcash. If other entities are working on that, we're happy to help them. We have some proof of stake and IBC experience. That's something we can offer. We could offer some engineering assistance. We could offer some design assistance. We are also willing to help directly. In order to do that, we need a much clearer understanding of what the Zcash community wants in some of these specific areas, kind of hence this presentation. And we've kind of hesitated on committing to an avenue in one of these two options because we really think the Zcash community's specific proof of stake plans make a difference, as in if proof of stake is something that will be done pretty soon, then a bespoke bridge doesn't make a lot of sense. If proof of stake and IBC are going to take a long time or kind of still under discussion, then a bespoke bridge in the short term might make more sense. So we're kind of still collecting information there. We're open to all of these avenues. Specifically, we're interested in kind of collecting further Zcash community feedback on what kind of staking and rewards mechanism people want, whether people would use a bespoke bridge or whether you would prefer to wait until Zcash integrates proof of stake and IBC support, and which potential benefits and uses of interoperability are most interesting to you. Questions, I think, will come asynchronously since I'm pre-recording this. And thank you very much. If you want to contact me, of course, I'll be around in the application, the Huva conference app for questions. And you can also reach me by email, on Twitter, or on the Zcash community forums. Thank you.
Hello, thanks for coming. What if private person-to-person payments were possible worldwide? What if 1 million people could pay each other all at the same time and all 1 million payments settled in seconds? What if every existing DeFi token on any chain could be wrapped for safekeeping in a Zcash shielded asset and saved privately in your Zashi wallet? What if you could hodl your ZAC, yet at the same time use it as collateral to take part in the vast world of DeFi across many chains? So these what ifs may seem far away, but these are the reason we are building the Zavex bridge. It is a building block toward worldwide adoption. Zavex is not the only possible path. There are other ways to accomplish these goals, and I believe a multi-pronged approach is wise. However, Zavex is a good one, and one that, in my opinion, has a high chance of success. Also, I believe that it's healthier for the Zcash community than an airdrop for a new privacy network because ZEC value will be preserved across the Zavex bridge, keeping ZEC strong. My personal mission in life, which I probably share with others in this audience, is to help the world shift its entire financial system from the current archaic, corruption-prone, painfully slow, inflexible status quo to a fully decentralized worldwide replacement. For this system to work, it must have these 5 characteristics: globally scalable, fast, inexpensive, private, and with gradated selective disclosure. Avalanche is designed to enable the first 3 in spades. Zcash enables the final 2. So for me, building this Zavex bridge to connect the 2 platforms was a no-brainer. It aligns perfectly with my own personal mission, and it's been on my mind for a long time, as you can see here. Back in 2021, I tweeted about it to Zuko. I wrote, which will come first? Zcash Foundation implementing Avalanche consensus, or Avalanche adding a copy of the Zcash blockchain as an Avalanche subnet? In the case of both Zcash and Avalanche, I had been familiar with each of these founders' work before their chains were launched. My previous startup had considered integrating Least Authority's Tahoe LAFS software, and for that same startup, I had approached a Cornell professor who would soon go on and found Avalanche for some advice about distributed systems, which he generously gave me. So imagine my delight to see each one help to launch their respective innovative and complementary cryptocurrency platforms. Okay, so let's look at where we are today. The first thing we did was to build a prototype, an oracle, which is a necessary element of Zavex. We built a 3-node permission subnet on Avalanche's Fuji testnet, whose sole purpose was to reach consensus on the contents of a Zcash block at any block height. I'll show you how it works. You just go to zavex-oracle.red.dev, and then you pick one of the 3 nodes to query, and then you put in a block height, and just copy and paste. Let's see here. Let me just type it in. For 9. This is from this morning. And in that quick time, the 3 nodes reached consensus and minted a new block on the Zavex Oracle subnet, And you can see it's a new block because the block height and this block match. And here's the contents of the Zcash blockchain at this block height right there. Building the Zavex Oracle allowed us to accomplish 3 goals. First, my team and I were able to familiarize ourselves with this brand new subnet technology of Avalanche in a way only possible when you actually try to build something useful. Second, a prototype provided a demonstration of Avalanche technology to the Zcash community, whose first reaction, of course, was skeptical. And third, it allowed us to learn the DevOps challenges of operating a subnet over time, security, uptime, upgrades, etc. Next, we designed the architecture documents. We had 2 goals in mind. First, because bridge design is so critical, we felt it important to be meticulous about putting the architecture into written documentation. Second, we knew that clear UML diagrams would allow other software developers and architects to quickly become familiar with the Zavex bridge and offer their critiques. And in the last few months, this has paid off. As we had hoped, the architecture documents did get the attention of experts, and soon I was having meetings with other top builders in the space. From these meetings came the next 3 deliverables. First, it was brought to my attention that while Avalanche, like Ethereum, supports BLS signatures, it does not yet support BLS threshold signatures, which we had included in the initial design. Luckily, the Zcash Foundation had just released Frost, so with the help of Paku, we have switched over to using Frost instead of BLS for threshold signing in our design. And by the way, we are also using Zebra. Second, some expressed concern about our design choice to encourage any Zavex Guardian to also serve as a connection point for the public. The technical term for this is an RPC endpoint. They had this concern because it's a blockchain best practice to insulate nodes as much as possible from attack. Still, for the sake of true decentralization, we wanted to encourage as many RPC endpoints as possible. So we are enhancing their security, and soon we will announce a white hat hacker contest to test these improvements. Third, in order to provide further evidence to the Zcash community that Avalanche subnets are reliable, we have added a one-click button to recheck and verify every single decision that the Zavex Oracle has made since its launch. This is available now at the bottom of the user interface that we were just looking at. So, as a decentralized bridge, Zavex's strength will be in its guardians. And for launch, it's important to have the guardians of the highest character. Over time, gradually, these guardians will cede control to whoever wants to buy enough of the bridge's staking token, ZACs, to become a guardian themselves. In this way, gradually, the Zavex bridge will become truly permissionless. I've been in talks with L1 founders and key organizations seeking their support. Though talks are still ongoing, one wonderful sentiment that I have heard more than once is that everyone loves Zcash. In fact, that's a direct quote. I think that in the greater cryptocurrency community, almost everyone understands the crucial importance of privacy and selective disclosure. And they understand that the uninformed and archaic regulatory changes that Dodger, Josh, Peter, Paul, and others have alluded to during this ZCon. So let me be clear, this is a call to action. There is strength in numbers. Just to give you an idea of what would be ideal, we would like Zavex Guardians operated initially not just by the Zcash Foundation and the Avalanche Foundation, but also by the Ethereum Foundation, the Solana Foundation, the Tezos Foundation, Bootstrap Org, Shielded Labs, and more. We could use the Zcash community's help, your help, in forming these connections. Concurrently, we will be building the software. We are writing it in the Go language because Avalanche's software is written in Go, and we will be utilizing API wrappers to interface with Frost, which is written in another language, Rust. This means that other Zcash projects written in Go will be able to easily copy our Frost implementation strategy in the future. We will then launch to Avalanche and Zcash testnets, and that will be the time for stress testing and auditing. Only once these are complete, we will launch to mainnets. We anticipate this happening late in Q3 of 2024. What? As a decentralized bridge, the more it is used, the stronger it becomes. For this reason, and because of the interest from the Avalanche community, soon after launch, we will add bridging from Bitcoin to Avalanche as well. Because of its $1.2 trillion market cap, even moderate bridging of BTC could greatly enhance Zavex's bridge security. Before we go, let me end with a little alpha, something no one has seen before. The Zavex Bridge UX is a deliverable for our next milestone, but we have already completed it. So let me finish up here by sharing it with you how it looked to use the Zavex bridge. So before using the bridge, you will need to have an Avalanche address set up in MetaMask, and you will need to have transferred some ZEC to a transparent address that is controlled by the same private key as your Avalanche address. In this way, your ZEC is wrapped into ZEC.Z using an address that no one but you controls, including the bridge itself. Legal experts take note. Then you just select how much ZEC you would like to send and to what network. Initially, you will be able to send to the Avalanche C chain, but we anticipate these options quickly expanding to other cryptocurrency platforms, especially with the support of other foundations. So you click continue. And here you confirm what you're sending. Click bridge now. Not shown, but at this point, MetaMask will pop up and ask you to confirm your intent. Your ZEC will then be wrapped. The main delay will be waiting for enough ZEC blocks to be written to competently confirm that your Zcash transaction was successful. This takes about 20 minutes. It's possible to speed this up in the future to near instantaneous by partnering with a DeFi insurance company on the Avalanche side. And then your wrapped ZEC.Z is available in your Avalanche wallet ready for use. By the way, ZEC.Z will be configured to automatically bridge with layer 0 and possibly wormhole to other DeFi chains, so your usage options are not limited to just Avalanche. I've just scratched the surface here so far. I think we have a few more minutes left for questions, so let me see if I can answer some. But before I do, I just want to, I love my entire team, but there are 3 members I want to give a shout out to for help getting this presentation together. Tommel, who is working on that security, that RPC security that I mentioned, he had to pause at a strategic point so I could do my live demo. And so thank you, Tommel. Oswaldo, DevOps, keeping track of making sure that everything's going to go smoothly as far as the demo went. And then also Ashmita, who not only designed the UX, but also helped me put together this great slideshow. So thanks to those team members. Okay, so let's see. Okay, first question. Do you think Zebra's current capabilities will be sufficient for the bridge, or will you need some additional functionality? So, okay. So when money passes from Avalanche, Zec.Z, back and is released as Zec, that's the most, we actually have to make a Zcash transaction to release that Zec, the correct amount of Zec. And so that, but we're going to be doing that with Frost threshold signatures. So, one thing that comes to mind is Zebra doesn't have a wallet attached to it yet, and we're waiting on that. But that doesn't really apply to us, because we have to sort of create that mini wallet software ourselves. So using Frost. And compose that transaction and then just submit it. So as long as we're able to submit that to Zebra, which as far as my understanding is you can, then we're in good shape. And basically we're using Zebra as an oracle. So, just as a source of proof of what has happened on the Zcash blockchain. Will transitioning to POS make the bridge faster than the 20-minute confirmation? Yes. So 20 minutes is a bit arbitrary and not finalized. As Christopher was saying in his talk just prior to mine, there is no finality with proof of stake. However, you get to the point where statistically it's more likely that the Earth explodes than the blockchain is wrong. And you get to that point in under an hour. So somewhere in there, you can, I think, from a human point of view, say this is final. Or, worst case, you can notice that there is a massive attack going on Zcash, where there's a chain split and many blocks. There's going to be a reorg in the future. You'd see a very fast increase in hash rate. So I've wrestled with this a little bit. How long do we wait? And 20 minutes seems like right now seems like a good number, but it might be 30 minutes in the long run. What you can do, and what I alluded to in the talk, is you can partner with an insurance company that provides you, as the bridge user, provides you with a little tiny bit of insurance for a short, like the shortest term insurance, basically 20-minute or 30-minute insurance that money is really going to get to you. And you would pay them a fee to do that, and we could integrate that into the UX, so it's just wrapped right in there, and you just check a box if you want to use that feature. And then you would get your Zec.Z right away. So that's another thing. But yeah, I mean, proof of stake is proof of stake can be partnered with faster consensus mechanisms. Okay. Oh, how can the community contribute to advancing the ongoing work on the bridge? Great question. Thank you. And I really appreciate that. And the community has been really supportive. For instance, Zcash community grants are paying Paku out of a separate stream, and they said, hey, he can help with this. So there's some awesome support right there, and it, that's just huge help. When we have this little hackathon or this little white hat hacker event, we really want this. We want to see if people can shut down this subnet, and if they do manage to shut it down, how shut down is it? Is there, is it a temporary distributed denial of service type of thing? Because we really want to launch a robust product. So there's another example. And we have a forum thread going, and I will definitely post when we can get help from the community. At this point with the software, I think we're in the too many cooks could spoil the broth kind of thing, but we won't be there forever. So as parts break off that could be, the software is open source, so anyone can contribute. But I think we'll really want contributions a little later on. So I hope that answers you. Thank you. Okay. Does Frost satisfy all of your requirements? Is there anything missing in the protocol or implementation? Out of curiosity, what threshold and number of signers are you using? Okay, yeah. So from what we can see, I had one meeting with Conrado, and then Paku has been revising our specs to include Frost, and everything looks good so far. Everything looks good, but we're going to have another meeting in the next couple of weeks, hopefully with Conrado and anyone else who's been working on Frost, just to make sure that we're understanding, there's a clear understanding of how this fairly new software works. But it looks good. And then threshold. So we're looking at a 70%. So the validators will have stake on them. We're calling the validators guardians. So they, in Avalanche, so let me back up here. And let me look at the time here. Yeah, we have a few minutes. Okay, so the Avalanche subnets are basically plug and play blockchains that are right next to all the other subnets and Avalanche's mainnet. And as such, the bridging between our subnet and the C chain is just effortless because it's pre-written by Avalanche using Avalanche Warp messaging. There's a product called Teleporter that Avalanche has produced just for the purpose of bridging. And I just shot a message after watching Christopher's talk about the IBC connections, because we may also, I think somebody else is working on that. There are a lot of people doing a lot of stuff on Avalanche. So, so that's how a subnet works. So there are two kinds of subnets. One is a permissioned subnet where maybe a bank or a consortium of banks wants to run 100 validators, but they want them for themselves and they don't want anyone else in them. Well, they set these validators up permissioned and they run them that way. And for our prototype, that's how we did it, because that's what's available now. But what is on the Fuji testnet are elastic subnets, where it's a permissionless subnet, where there's a staking token, and then you can set up your set flexibility about the rules that you can set up. It's really broad, extremely broad. It's a container, and indeed you can run other virtual machines. It's a common use case to run an Ethereum virtual machine inside a subnet, but we are not doing that. We're writing a custom virtual machine that's only purpose, it's written in Go, and its only purpose is to do this bridging. That's it. And then the money ends up, the ZEC.Z ends up on the C chain in this version 1. So, okay, so to answer your question, 70% to move funds, a 70%. So we need a 70% threshold of stake to move funds. So, and because you can't just say this guardian has 10 votes and this guardian has 5 votes with Frost, we actually have to give the guardian with 5% 5 votes or 50 votes, and the guardian with 10 votes 100 votes, and then the threshold is 70% to actually move money. So that's it. And don't hold me to that, but that's what's been sort of settled in our minds as a safe number. Okay, let's see. If I want to use the bridge, do I need a separate AVAX wallet, or can I use the derivation path for the wallet I already use for ZEC? Okay, so when you have a ZEC wallet, it's really just a private key, right? And so that private key can be used, you're using it for ZEC, but it could also be just as well used for Avalanche or Ethereum, and maybe you already understand that. So forgive me if maybe other people in the audience don't, but that's the case. So you really already have an Avalanche wallet. You just don't know the address probably. So yeah, you could use that. Sure. We'd actually recommend that you create um, a separate wallet just for, I don't know. It's just a little clearer about what's going on. But that would be supported. Yeah. Um, let's see. Okay, let's see. If here, I'm gonna just take a sip of water here. Okay. If Zcash was available on MetaMask from a MetaMask snap, which has been proposed to the ZCG by ChainSafe team, would that improve the UX of Zavex bridge? Yes, sure. And if we want to, that would be a great, there's a partnership opportunity right there, because uh, we're going to have to write a snap. We can write a very, very simple snap, but we have to write a very, very simple snap in order to get MetaMask, because MetaMask at the very, very, very bare minimum needs to sign a Zcash transaction, and then to put in a user interface on top of that, make it nice, and have a whole bunch of different functionality. Yeah, that'd be awesome. Yeah. So I haven't talked to anyone on the ChainSafe team. Let's get in touch. So that would be cool. All right. Well, hey, listen, thanks everybody. We're really excited to be working on this. My call to action, please take heed of that. I assume some people in the audience are on the Zcash Foundation, on the Avalanche Foundation, on the Tezos Foundation, and on the Solana Foundation. And I hope we can all work together to secure this bridge as it's launched. It just makes it's good for the ecosystem, it's good for Zcash, and it's just we all know that we need these parts of privacy and selective disclosure. Those are key elements of building this decentralized financial system, and for the whole crypto community to be saying, yes, this is important, and yes, we support that, that would be a great thing. So, all right, well, thank you very much. Appreciate your time, and hi from everybody at Red Dev, which is the name of the company building Zavex. Okay, bye.
Hi, everyone. Thanks for joining us today. My name is Jason McGee, and I'm here representing Shielded Labs. I'm joined by Tomek Petrowski from Eiger, and today we're going to provide an overview of the Zcash Sustainability Fund. We'll discuss its objectives, how it functions, and the current status of its development. And we'll also cover the implementation process and our anticipated timeline for completion. Next slide. So recently, there's been an increased attention around Bitcoin's future security budget due to the possibility that miner revenue from transaction fees may not be sufficient to provide network security after the block subsidy ends. The concern comes from Bitcoin's decreasing block reward schedule, which halves every 4 years. As the block reward diminishes over time, the incentive for miners to secure the network relies increasingly on transaction fees. However, if the volume of transaction and the fees associated with them do not grow to compensate the reduced block reward, the security of the network could be compromised. This could lead to a reduction in the number of miners, resulting in decreased network hash rate and increased vulnerability to 51% attacks, where a single entity could gain control over the majority of the network's hash rate. So Zcash faces a similar problem, as it's a fork of Bitcoin with a network that's sustained by block rewards, and it operates with a supply cap of 21 million coins. So the Zcash Sustainability Fund is an attempt to address this issue of network security. It's a modification to the issuance mechanism. It maintains the 21 million coin cap and enables deposits of ZEC from the circulating supply into future block rewards in order to sustain the network. It's compatible with proof of work or proof of stake, and it's an important step for future economic upgrades like Zcash shielded assets, and it has other use cases like protocol fees and other user applications. Next slide. So before we get into the details of the project and how the Zcash Sustainability Fund works, let's start with some background. I'll explain how the project was originally proposed and how Shielded Labs, along with Eiger, came to spearhead its development. So the Zcash Sustainability Fund was originally named the Zcash Posterity Fund. It was proposed by Nate Wilcox, formerly of the Electric Coin Company, in August 2022. And in a blog post, Nate outlined his general vision for the project. He said the Posterity Fund would replace the current Zcash issuance mechanism with a new mechanism that preserves the 21 million supply cap and smooths out the emissions curve while maintaining an approximate issuance rate that replaces the 4-year halving cycle. It also introduced the new mechanism that allowed for deposits into the fund to be distributed over time in future block rewards. There was some community discussion around the project, but it never made it onto the ECC's roadmap, as there were other engineering priorities that took precedent. These included things like delivering world-class UX and for Zcash and also proof of stake. And then in 2023, I established Shielded Labs as this independent Swiss-based Zcash organization. Its mission is broad. It's to increase user adoption, develop new use cases for Zcash, and contribute to protocol development. There's 2 primary reasons I created Shielded Labs. It was one, to increase decentralization by having more organizations contributing to Zcash development, and second, to make Zcash more resilient by having more geographic diverse ecosystem. So Shielded Labs chose the Zcash Posterity Fund as its first project for a few different reasons. First off, it aligned with our commitment to contribute to protocol development. Historically, protocol development has been handled by the Electric Coin Company and the Zcash Foundation, and we like the idea of a network upgrade being initiated by an independent development team. Second, from a technical perspective, we saw the project as sort of low-hanging fruit and relatively easy for a small team to implement. Overall, it seemed well worth the effort in terms of the benefit it would bring the ecosystem. And then third, we thought it provides an opportunity for Zcash to continue to improve on Bitcoin's design. So if you think of privacy and the development fund as 2 important features that define Zcash's identity and differentiate it from Bitcoin, the Zcash Sustainability Funds allows Zcash to sort of continue that tradition by providing a mechanism for long-term network security. excuse me, we hired Eiger, which is part of the Equilibrium group, to lead development. I was familiar with their team as a member of the Zcash Community Grants Committee. They've received a few different grants for Ziggurat, which is this network test suite for Zcash-D and ZebraD nodes. And I knew they had a proven track record, and they seemed like a good fit to lead technical development for the project. And then lastly, we changed the name to the Zcash Sustainability Fund because we felt that it reflects its purpose of, ensuring long-term sustainability of the network. If you like, sustainability kind of gives this idea of maintaining the network's viability over the time, whereas posterity is more about like future generations and doesn't capture the idea of ongoing support for the network. Next slide. All right, so what is the Zcash Sustainability Fund? Well, I think the best way to answer this question is to say what it is not, because it's often misunderstood due to its name. So first of all, the ZSF has nothing to do with the Zcash Development Fund that goes to ECC, the Zcash Foundation, and the Zcash Community Grants Committee. It doesn't finance specific projects or development efforts. Instead, it functions as a protocol mechanism to help support the network. Second, it's not an organization with a staff or administrative structure, and it's not controlled by an organization. No one owns or manages it. It operates according to, predefined rules set within the protocol. And then lastly, despite its name, it's not a fund in the traditional sense. You can think of a fund as a pool of money managed by individuals or like invested in assets, and there is no fund. The ZSF it's not held in a pool like the Orchard pool. It's essentially unissued and accounted for via the consensus rules. So it's a mechanism within the protocol designed to ensure the long-term allocation of these resources for network security. So then what is the Zcash Sustainability Fund? As I said earlier, it's really best to think of it as a modification to the issuance mechanism that maintains the 21 million coin cap and enables deposits of ZEC from the circulating supply into future block rewards in order to sustain the network. The new issuance mechanism mirrors the payout rate of the original issuance mechanism over a long period of time. And there are a number of different use cases that this change enables that can be implemented by the community in the future. But before we get to that, I just want to discuss what happens upon implementation. Next slide, please. So what happens when the ZSF is activated? So upon implementation, the current ZEC issuance mechanism is suspended and replaced by the ZSF. In each block, the ZSF payout is distributed to block reward recipients, and then users, applications, and other protocol extensions can make deposits into the ZSF. With regards to the payouts, there's a limitation in that the ZSF payouts, which approximate the 4-year half-life, and the payout rate cannot be increased beyond that 4-year half-life constraint. So future protocol changes have to adhere to that limitation. Our proposal, I like to call it modest, in that what we're doing here is we're really just building the underlying technology for the Sustainability Fund, and then we're leaving discussion to disbursements for the community to decide after it's been implemented. We're intentionally neutral towards block reward recipients so that the implementation of the ZSF doesn't happen at the same time as decisions about how to disperse, the allocation. So what that means, for example, is if the ZSF was activated today, then the distribution of newly issued ZEC in block rewards would follow the split outlined in ZIP 1014, where 80% is allocated to the block miner, and then 20% gets allocated to the dev fund recipients, ECC, ZF, and ZCG. And then at the start, the ZSF is just funded by a percentage of transaction fees that's actually very, very small in terms of ZEC. But before we get into that, I just want to take a step back and talk a little bit about how the ZSF is designed. And I wanted to talk a little bit about the ZIP process and the 3 ZIPs that govern the Sustainability Fund. Next slide, please. So Zcash improvement proposals, or ZIPs, are the way to propose new features to the Zcash protocol and explain their rationale, specify implementation details, and document design decisions. You can think of the ZIP as like a technical specification that details its functionality or a project's functionality and explains how it operates under the hood. For this project, we have 3 ZIPs, and I'll briefly explain their purpose and the motivation behind them, and then Tomek will provide more technical details later in the presentation. But the first ZIP establishes a sustainability fund at the protocol level, and it allows funding from sources other than newly issued ZEC. Key proposed changes include maintaining a global balance at the consensus level called ZSF_balance, and it's tracked as a node state. And then we also add ZSF deposit field in transactions to facilitate contributions to the fund. The second ZIP smooths out the issuance curve by modifying how the block subsidy is calculated. Rather than adhering to Bitcoin's 4-year halving cycle, it proposes this exponential smoothing of the issuance curve that maintains the 21 million coin cap. We do this in order to sort of enhance the economic stability by making the distribution of block rewards more predictable and consistent over time without altering the issuance policy. So you don't get that shock that occurs every 4 years during the halving. And then the third ZIP deposits 60% of transaction fees into the ZSF. Now, it sounds like a large amount, but transaction fees are so small that we're confident that this would not, upset or shock miners. We were originally going to propose 90% of transaction fees to go to the ZSF, but we felt like optically it might be misinterpreted as a harsh tax on miners, despite it being a small amount. So the 60-40 split seemed like a relatively fair and neutral way to split transaction fees that would allow us to, allow the ZSF really to start accruing small amounts of ZEC. And now I also want to say a little bit about the ZIP process, because that was very interesting to work through. The process of writing and revising a ZIP can be very time consuming. Initially, we expected the ZIP process to take about 2 months, but it ultimately took more than 6 months. There were a few different reasons for the delays. First, it took us time to research and understand the protocol level changes required to establish the ZSF. And then second, the ZIP editors meet every 2 weeks, which introduces delays between receiving their feedback on a draft, making revisions, and then getting more feedback on those revisions. And then additionally, there's only so much attention or time that the ZIP editors have, and they often have to review other projects like the Zcash shielded assets, and that can affect the timeline for feedback for our project. But having said that, the ZIP editors were extremely helpful and very approachable. We have a dedicated communication channel on Discord where we can ask them questions. They always respond in a timely manner. But their official and collective feedback, as well as the more or less approval of ZIPs, happens during the biweekly meetings. And then lastly, I want to mention that in our experience, the feedback from the ZIP editors focuses solely on the technical aspects of the ZIP. So they consider things like whether the proposal is focused and compatible with the existing protocol. Are there any security flaws? Does it conform with the requirements of existing ZIPs? And ultimately, is it something that can be implemented? So in our experience, the editors they don't offer their personal opinions on the project or whether they support or oppose the proposed changes, unless, we specifically ask for that feedback. Next slide. So next, I want to go over a few future use cases for the Zcash Sustainability Fund. As I've mentioned, we're proposing contributing a small portion of transaction fees to the ZSF, but there's a number of future changes that could facilitate additional deposits into the fund. And this again isn't our decision, nothing that we control. All of these would have to be ratified and approved by the community. So the first one is donations in ZEC. Donating into the ZSF is a neutral way to contribute to the sustainability of the network without favoring any specific organization or individual. Wallet apps, for example, could give users the option to donate to ZSF when making a transaction. This is something that can happen right off the bat. There are also donations in other assets. Like if you remember when Chris Goes from Namada announced a strategic alliance between Zcash and Namada, one thing that he mentioned was contributing NAM across a bridge to the Zcash ecosystem via the Sustainability Fund. So I think that's an interesting use case for it. Next are legacy support fees. So these can be instituted so that users relying on older protocol technology can compensate the network for the risk and cost of supporting that older technology. So like an example of this is, there could be fees for users storing their funds in an older pool. And this might incentivize them to move their funds into the new pool. Then Zcash shielded assets. So there are a number of applications here, like a portion of the fees associated with minting, destroying, transacting, or storing ZSAs could be deposited into the ZSF and contribute to the network security. So if somebody holds shielded Bitcoin, or as we call it, ZBTC, they could pay a percentage of their stored asset into the ZSF, sort of to give back to Zcash. And then privacy incentivization fees. So these could be introduced so that users who transact or store their ZEC and T addresses compensate Zcash users for the opportunity cost of a larger anonymity set. And then there are Ethereum EIP 1559 style fees. There could be a base fee transaction fee mechanism that automatically adjusts based on network congestion, and where a portion of the fee is redirected into the ZSF. And that could provide a consistent and predictable source of funding. Okay, so now I'm going to pass it over to Tomek, who will discuss the technical details of the implementation.
All right, thank you, Jason. So as Jason has pointed out, the ZSF is a three-part effort. So it was split into three separate Zcash improvement proposals. And the first one is the ZIP 233. So this ZIP is really just about setting up, establishing the ZSF as an entity in the protocol. And it does this by doing two things. One is it creates this concept of a ZSF balance inside of the protocol, and then it creates ways for users and miners to donate to this ZSF balance. So what's important to understand is the ZSF balance is not going to be a Zcash address, right? So this is in contrast to, for example, how funding streams currently work. So if you look at the Zcash node code, funding streams are actually just plain Zcash addresses that are hard-coded in the Zcash node code base. So it's not going to be that. It's also not going to be stored anywhere in the blockchain. So the balance itself will not be visible anywhere in the block. It will have to be calculated and stored by each node. So basically, blocks and transactions will contain ZSF deposits, and if a node will want to know what the current ZSF balance is, it will have to go through the entire blockchain and calculate the current ZSF balance based on that. And the ZIP also introduces two ways of making ZSF donations. So the first one being from traditional non-Coinbase transactions. And this is done using the new ZSF deposit field. And the second way is using Coinbase transactions. So this is something that miners could use to donate to the ZSF, and they can do it by not claiming all Coinbase transaction inputs. So basically not spending all the coins that they could spend. So the the ZSF deposit field will be added to transactions, to the transparent portion of the transaction entity. This will, of course, necessitate the introduction of a new transaction version 6. And basically, as I said, every transaction will be able to make a deposit using this field. So a maintainer of a wallet would basically allow the users, while creating a transactions, to make a deposit using this field by specifying a non-zero value in there. This, of course, affects things like transaction serialization IDs and hashes and related things. So these things will also need to be updated. And using coin-based transactions, what miners could do is they could not spend all available coins that they could spend in a coin-based transaction. So miners, when creating a coin-based transaction, they can spend obviously block rewards and transaction fees. What they could do is not spend all of those in their transaction outputs. So if the outputs will be smaller than the sum of things that they could spend, this will end up in the ZSF deposit. And curiously, this is something that has already happened in the past. Is it due to a technical error or on purpose? I don't know, but if I remember correctly, somebody from the electric coin company has reviewed past Zcash blocks and has found out that there are blocks out there in which miners did not claim all possible rewards. So this really resulted, up until this point, resulted in basically burning those coins. They were unavailable to the protocol. It was not possible to mine them again. And what's important to understand with this new definition of the ZSF deposit, those coins will get, we can call it unburned, right? They will end up in the ZSF deposit rather than being completely inaccessible. So this is something to be aware of. This is, of course, not a lot of coins. This didn't happen often, but yeah, it's good to be aware of that happening. So the second zip 234, is about smoothing out the issuance curve. So what we do here is we create a new function that, given a ZSF balance Z, will output a block reward. And this function needs to satisfy certain requirements because we do want to preserve the kind of the contract we have with the Zcash users currently. So obviously we don't want to accelerate the rate at which the coins are issued long term. So if we think about it, this function needs to be monotonically decreasing, right? We want this deflationary component of the Zcash protocol to still be there. And to satisfy this requirement which Jason mentioned, which is this mitigation of economic consequences of a halving, we want to make sure this function is more of a continuous function, right? It doesn't have those rough edges that halving produces. We want it to be more of a continuous function. We want it to be more than 0 if the ZSF balance is more than 0. So we don't want any funds to be stuck in the ZSF. And of course, for any 4-year period, the sum of all paid out block rewards, it needs to be equal, more or less, to half of the ZSF balance at the beginning of that 4-year period, right? So we want to maintain that part of that property of halving. And it turns out, if you define a number, 4,126 divided by 10 billion, and you multiply any number really by this number, and calculate, well, if you calculate block rewards using this way, and you do it for a 4-year period for every Zcash block, then you will end up with 50% of the funds you had in the beginning. This is, of course, calculated using the property that 1 minus this number taken to the power of the number of blocks in a 4-year period we'll give you 50%, we'll give you a half. One extra thing that we do here is we round up. So this is to satisfy this requirement that we always want to have non-zero block rewards if the ZSF balance is non-zero. So this is what you end up with. Here you can see block subsidies paid out in a period of a bit over 20 years here. The blue line is the current issuance scheme, and the red line is the ZSF smooth issuance. And what you notice here, the red line is more or less continuous, and the sum of block rewards paid out in a 4-year period matches what it would what would be paid out with the current issuance scheme. Another thing you might notice is block rewards in the first half of the 4-year period are actually higher than they would be with the current issuance scheme. This is something that some of the community members have been a little bit skeptical about, because it introduces this a little bit of a inflationary pressure which otherwise wouldn't be there. We could mitigate this if you look at the graph by moving the activation time by 2 years forward. This would actually introduce more deflationary pressure at the beginning. So immediately after activation, we would actually have less coins mined rather than more coins. If you want to play around with this, we have a tool online available on GitHub, and you can play around with the parameters and see how they affect the issuance and what other possible implementations we could have. And the last zip, zip 235, is about the 60-40 transaction fee split. This is really straightforward. What's important to understand here is that it is highly probable that this would be released either with or after zip 317, which redefines the way that transaction fees are calculated. Zip 317 makes the transaction fee dependent on the number of transaction inputs and the number of transaction outputs. So anytime you want to understand the consequences that this change would have on the protocol, you need to make sure you are looking at it under the zip 317 regime. And again, we have a tool that simulates this, or rather estimates the impact this would have on miners. And the estimated impact of this per year would be 210 coins. So this is not a lot. If you look at the current ZEC price, this would be anywhere from $4,000 to $6,000 per year. So it's not a significant sum. And so what is the current implementation status of this? The Zcash improvement proposals are ready for community review. So they are available on GitHub, and they have been mostly unchanged for the last couple of months. So feel free to review them and share your feedback. We have started implementing this on ZebraD, and that implementation, I would say, is around 60 to 70% complete. And we have a few weeks of work remaining there. We haven't started the Zcash implementation yet. It should take around 12 weeks is what we estimate. All right, I'm gonna hand it off to Jason.
Yeah, so a big part of the project outside of the technical development is building consensus and demonstrating community support for this change. We first started collecting sentiment on the forum last year, and overall, the community was pretty supportive of the change. There were some questions and some criticisms that came up, but I think we did our part to sort of address those. How we demonstrate consensus for this project is a little unclear. There are mechanisms like Zcap that the Zcash Foundation uses to pull the community. ECC just introduced their ZAC, but because we're a different organization, or Shielded Labs is a different organization, we don't want to rely on the ZF or ECC's method for gauging sentiment. And I think at the end of the day, if we issue upgraded software that contains a ZSF and enough Zcashers choose to run that software, then that should demonstrate the collective consensus of the community. But we really want to make the effort to know what the community thinks. And so our call to action is to encourage community members to voice their support or opposition or ask any questions about the Zcash Sustainability Fund. There's a thread on the forum that you can use to provide your feedback publicly, or you can reach out to me via DM on the forum or Twitter if you want to let me know what you think privately. And then one thing I'd like to occur is Shielded Labs intends to experiment with other methods of determining consensus. So one idea I've been thinking about for the past few months to a year is that the Zcash community has grown over the past couple of years, and a number of these distinct sub-communities have emerged. So each has its own sort of interests and perspectives. So examples include Zec Hub, Zcash Global, Zcash Brazil, other vibrant communities in Russia, Venezuela, South Korea. So what I would like to do is ensure that the perspectives of these sub-communities are represented, and the way I think that this could work is that each sub-community could have a representative that's responsible for polling its community and gauging their opinions, and then could report back to us. So I'm sort of thinking about calling this a Zcash Community Council, and I will over the next couple months sort of give a little bit more detail about that. And I'll also be reaching out to the communities as well. But yeah, I think if, let us know what you think in the meantime. And if you have any ideas for ways we can better engage the community, please let us know. Thank you.
So we have a question. Do you want me to answer it, Jason?
Yeah, go ahead.
So the question is, there is a lot of confusion regarding the smoothing of the